Okay, it's not this one I want to share. Yes. Sometimes I want to expand I want to make the screen full.
So what does the KR20 and KR21 mean?
Where is well, I myself I don't maybe there is one. It should be the version because the KR is Kuda Richardson. No, there are two of them, Kuda and Richardson. Okay. Yes, maybe I've not found out, but I think it has to do with they propose a method they have and improve. They have two versions anyway. So two versions of that. And I've already said that I didn't want to go into the room. You can go and search out. No, it's not only that we have Gottman, we have different methods. We have told that the peak of it is the Chromback, and that is what is most popular because all of them try to improve on that split half, and eventually it's Chromback that actually did the best job at the end of the day. Though everybody worked very well, but of course, Chromback now was able to ride on what they have done before to now come out with the best. We would think the best for now because they are taking every item into consideration. So what I just want us to quickly look at is the percentage agreement. This agreement here, I'll just say scoring agreement. So you see that scoring agreement, I said that from what we have now, we just have 4 different approaches to reliability, determining reliability. One of them test with we have equivalent form, we have internal consistency, and we have scoring agreement. It's under the scoring agreement we have the inter-rater percentage agreement, and that is also where that one fits into because the Bland-Hartmann is a form of way to ensure that 2 measurement methods agree. It's just agreement. So you see that agreement of 2 measurements is just one aspect, one way of looking at reliability to see if a particular maybe 2 method or a particular method of data collection and is reliable. So we said that the different methods, each of them come into play based on peculiarity of the situation. So there's no situation where you need to use all of them. So the best you can even do is to use 2. No overlap, maybe you do internal consistency and another one or another. So the best to require 2 of those methods. So there are situations that it's only one that is required in the particular setting. So Martin, Bland, and Douglas-Hartmann introduced this plot to describe the agreement between 2 quantitative measurements. And they are what they first published it in Lancet some years ago. They established a method to quantify agreement between 2 quantitative measurements by constructing limit of agreement. What we are saying here is that you have a method, you have 2 separate methods of measuring the same thing. So I have 2 examples. What I made to you is 2 examples. I have a bilirubin method, measuring bilirubin. We also have potassium. There are 2 methods of measurement just to estimate bilirubin. This bilirubin is the work of somebody, part 2, in National Hospital, a pediatrician who tried to estimate bilirubin through total serum bilirubin or transcutaneous estimation of hyperbilirubinemia. So estimating hyperbilirubinemia through measurement measuring bilirubin levels in the serum or using transcutaneous. There's something they just do and to measure if that was invasive, you don't need to bring the blood out. So they try, of course, you know that one is better because does not require taking the blood. But in trying to see if it's actually at the measurement, what do I call it? So he tried to validate anyway. He wanted to validate it. And one of you, of course, if we have already said that for a system, before a system can even be valid, that's first of all reliable. But it doesn't mean if it's reliable, doesn't mean it's valid. So in trying to validate a particular method, you may have to do reliability. So now they now ask me to, okay, do plots, Bland-Hartmann plot, because that one will serve as a measure of reliability in that study. But so if you look at it, quantitative variable. So what if the variable is not quantitative and it has to be measurement that has the same unit? That's another thing. So like in this case now, it's bilirubin. You measure bilirubin milliequivalent per liter. In both method measure the same thing. But if you look at what do I call it? Correlation. There are some situations where you are estimating something and the two methods they don't have the same unit. If the two methods don't have the same unit, it doesn't. Two methods don't need to have the same unit before they can do the same thing. So in that case, you cannot use it. You cannot use that method. So one thing, the superiority of what do I call it? Correlation, in this sense that correlation is more universal in the sense that it has no unit. If you remember when we discussed the origin of correlation, how you determine, you got correlation from a covariance. Correlation is a standardized correlation. Covariance. Covariance is just like, because it has to carry unit, you know, it's affected by the unit of measurement, but by the time you divide by the product of their standard deviation, it cancels out. So you can correlate age and a score. You can correlate anything that quantitative. They don't have the same, need to have the same, and the unit will not come irrespective of the unit. So it's not determined by the unit of measurement. So that is where the correlation is better in a situation when you now have a quantitative variable and you have two methods of measuring and they are having the same unit. That two methods, they measure in the same unit. So it is advisable that it is better to now use Bland-Hartmann. So yeah, to check the assumption of normality of different and other characteristics, they use a graphical approach because they plot the graph. What do they do? You take the measurement using two methods and now calculate the average. You add the two and divide by 2. That is the average. And you remove one from the other. That is the difference. So you now plot the difference on the vertical axis and the average on the horizontal axis. So the average now is representing, of course, that particular thing for the value of what you are measuring. Since you use the two methods, it makes sense to, okay, you cannot choose one to the detriment of the other method. You can now add them and calculate the average. So you can say the average actually stands for the value of that measurement. But to see that if the difference in them, how does it vary along the average value? How does it vary? As the average increases, does it affect the difference in the measurement? And that is what we just did. And perfect. So before look at the example. This one I plotted, even the two you're going to see, I plotted them. Because this is what I plotted for the person. And if you look at it, the bilirubin, so okay, I was making correction, okay. Yeah, okay, yes, that's it. So the bilirubin, look at it. The average is plotted along the horizontal, while the difference is plotted along the vertical. Of course, if actually there's no difference in the measurement, you expect the difference to be 0. If all of them throughout, they have the same value, the difference should be 0. So if you plot, of course, when you plot it, there will be some where like this one, we have two methods, the total bilirubin, serum bilirubin, and transcutaneous bilirubin. So there will be some time for a particular person, total serum bilirubin may be higher than the transcutaneous. For another person, transcutaneous may be higher than total bilirubin. So at the end of the day, if you do t-test, pair t-test, what will give you, if actually there is no difference, the average of the difference will be 0. Because what it means that if you, irrespective of which one you remove, either you remove TCB, the transcutaneous from TSB, total bilirubin, or you remove total serum bilirubin from transcutaneous, whichever way, some will be positive, some will be negative, because unless if persistently there's one that has higher value. If persistently maybe a total bilirubin has higher value, what will happen is that if you remove TSB from TCB from it total, you throughout you get positive different. If you remove it from TCB, you get negative different throughout. But in a situation where you are some are positive, some are negative, irrespective of which one you remove. So if you now calculate the average, it will be 0. And if average is 0 or close to 0, if you do t-test, there's no significant difference. It shows that there's no difference, even t-test. So this one, what they just do is just using t-test, but to create a pictorial view. That is why they plot a graph, because there's no statistic attached to it. The only statistic you can do here is pair t-test. But then when they create that picture now, you will see that, look at this one now. The difference, the mean, you now calculate the mean difference. The mean difference is the line that is just above 0. So the mean difference is 4.2. But if I tell you, if let's say we have removed, it's the other way around. We remove the, because in this one, what we did was to remove TCB, total serum bilirubin from TCB, from transcutaneous. If we have done the other way around, what will happen is that the mean difference will be minus 4.2. It's just below 0. This one is just above 0 now. If you have removed the other one from it, will give the same thing the opposite way. So now, what we now do now is that you now, the standard deviation of the difference. The standard deviation of the difference now, you know, okay, 95% confidence interval. That would be 1.96 multiplied by the standard deviation. That is, either you use 2 standard deviation, or to actually get the 95%, 1.96. If you now multiply 1.96 by the standard deviation, you now plot it. That is when you add it, the plus is the 54.6. That is the mean plus 1.96 standard deviation is 54.6. Then the one down is minus 4.6. When you remove that 1.96 standard deviation from the mean, it gives you minus 46.2. So you will now see that most of the different, the plot now is in between the two lines. So it's only few. But you will notice something, because the conclusion the person made in his study was that, before you get to anything below 150, if you can see that, anything below 150, look at the average, 150, there's no value that is outside the 95%, because that 95 within that, plus or minus 95, that 95% in between, in the middle, is accepted as the limit of agreement. So if the agreement, if the bias, because the difference is the bias, what we are plotting here and the verticals is the bias, is the difference. That is, the bias means the difference in the right, in between them, in the estimation between them. So now the limit of bias, that is, normally it should not be, it should be within that 95%. Anything outside, it believe that it's not good enough. So you see that there's no one that falls outside that limit until the thing reach 150. So what it means, because even in the process, because that's not what we are discussing now. Even in the research work, we discovered when we did, anyway, we may see mention of it, when we did the validity, sensitivity, specificity, we discovered that at low value, the reading of TCB, the transcutaneous, is very, very close to that of total serum bilirubin. But once the thing is becoming high, you begin to see difference. And that is what it has shown in this figure now. It is after the thing is above 150 that you begin to see value outside the limit of agreement. So you see, what is the summary? The mean bias plus or minus standard deviation between the two bilirubin level is 4.2 plus or minus 0.26. Sorry, I made mistake here. It's on. I didn't change. I was changing something. I remember to. It's 25. The 25.7. The standard deviation is 25.7. 25.7. When we now calculate 1.96 of the standard deviation, we remove, we add plus or minus, it give you the range. It will be minus 4.46.2 and 54.6. Now, another example. Okay, Iguilo, you raise hand. Go on.
Yes, sir. Okay. No, my question was like still on that former graph you were showing us. You said that once it is below 150, like I didn't
It's
get
not
the
the
graph,
former.
but the
Is
graph
not
is
that is still the graph I'm showing now. It's not the former graph. I'm still showing the graph. Okay,
I'm
no,
still
sorry, this
okay.
former one.
I'm still trying to
Sorry.
understand
So
this
I
one.
want to
So
correct.
that if it is
I want to
below,
correct. I want to. Sorry, I want to correct the wrong thing. Go on, speak on, speak on.
okay. I wanted to show me that I was to put it on that graph because you said that once it is
No, I will
below
show you. I will.
150.
Don't worry. Demonstrate. That's why I send the. I send the something that I send it to you, to everybody now.
I've got downloaded it. I've downloaded
I
it.
send it. I send it to everybody. I almost it's two of them. So okay, I think I was.
Okay. No,
Okay, this is what
okay,
I
because I'm
wanted.
trying to understand it. Like it would be nice if you had visualized it with those your markers. I know you said the 95% confidence,
Don't
that's
worry.
the
When we
the
will
the
run it now.
interval.
We will run it now. You understand it better. I will just give you a preamble. Oh, it's raining heavily here. Okay, my speaker. Okay, I think we can go ahead and quickly run it so that I can explain because we have two samples so that we won't waste time. But it's good. It's good to know because it's a. If you look at it, this is it's exclusively to me, even being used in the medical line because it's not as universal as the correlation because most of the time the people that publish anyways from medical literature and it has to do with quantitative measurement when you measure quantitative variable with two methods, different methods. Now, bring the light for me. Okay, I think we can quickly share. Maybe I should share my own. Has anybody opened it? So that if you open it, you can quickly share. Has anybody downloaded what I sent? Give me light. If nobody, let me share my own. Yes, I don't know if anybody can see. I'm shouting, sorry, because hope you can hear me because here is heavily, it's raining heavily. Everybody see what I share?
We can hear, we can see.
Yeah, you can see.
I can hear, I can see.
Yeah, thank you. This is the data set, the TCB total serum bilirubin, then transcutaneous bilirubin, then the average bilirubin. That is when you add the two together, divide by 2. So this is the average of the two value, and this is the difference. And the difference, what did I do? I remove the total serum bilirubin from transcutaneous one. It doesn't really matter which one you remove, but you just look for the difference. Now, you can actually do this one even here or with Excel to remove how to, if let's say you want to do the average, all you need to do is to go for, let me just, so that, because Dr. Ikobo, has Dr. Ikobo joined? Is he around? Is Dr. Ikobo there? He has not come.
He's around, sir.
Okay, he's here. He's not answering me. Okay. Let's say.
I think Ikobo
yes.
is around.
Yes, I've seen him. So let's say you want to calculate the average. Very simple. How I calculated the average. You just go to transform. compute. I just say average bilirubin. So if you say average, all you need to do, okay, just bring your bracket here and just move TCB, move it, TSB plus TCB, you move this one, slash, divided, that is divided by 2. That's all. If you look at it, because I'm dividing both of them after adding, that's why I first of all bring out the brackets, so that when you add it, before you divide, you remember board mass. Brackets. What is in bracket first? Operation in the bracket. So that's that you have to first of all add. But if you don't put bracket, it will just divide. It will go and divide TCB by 2 and now add it to TSB. But that's not what you are doing, looking for. You are looking for the average. You want to add both of them before you divide. That's why you have to first of all put bracket to put them inside bracket. Then before it will add it, the computer will add it then before you divide. When you do that, you have created it. If I let me show you, because can you see now? Can you see average? It's the same thing we have here. Can you see the average? That's how I created the average. So if it is different, the same compute, transform, compute, there's a difference. Diff. So diff, T, what I did was TCB minus TSB. You move TSB in. That's all. So if I, can you see? Can you see the difference? And if you want to make it, that's what I've got here also before. If you want to, if you do it the other way around, you say you make the difference, you put this TSB first before TCB. Let's say different 2 now. In another way, TSB minus TCB. So you see, can you see the difference? It's the same difference, but the only thing is the sign will change. Those that were negative become negative, positive. Those that are positive will become negative. It's the same thing. So let's now see the way we plotted it. You just plot graph. When you go to your graph, go to graph. You can use graph builder or use legacy dialog, any of them. If you want to use the graph builder, you just click on it and say okay. Then when you come here, you are looking for, first of all, the number 1 there is bar chart. You search scatter plot. It's scatter plot you want to do. You click on scatter plot. When you click on it, now drag that first one, because that's the simplest scatter plot. You drag it to this place, to the space. When you drag it, can you see? It gives you the y-axis and x-axis. You know what you are plotting on the y-axis. The y-axis is the difference. So different. You now drag it to the y-axis. The mean average. The average is the x-axis. You drag it. You say, okay. I don't know. Let me share the output. You may not be seeing it. Can you see the output now? Can you see the output? Please, somebody should respond if you can see the output.
Yes.
Yes, okay. Now, if you look at it,
You can see the output.
yes, it has not shown us, you now need to edit it. It has not shown us, but it just show you the scatter plot. This is not a regression line. That's why it's not going up, because this is the average and the difference. So it will be horizontal like that. Because the best you can get is to calculate the mean of the difference. So that's why it's not if it's a regression line now. If let's say it's not the difference we calculated, you will see the way both of them will go up. Now you double click. This is viewer window, this is result window. Then there's what we call chart editor window. For you to enter into that window to edit your chart, you double click on the chart. When you double click on it, can you see it opens the chart editor window? That's open and that window. Just like in your room now, you open the room door to your toilet. It's another room inside your room. So this is a window. When you double click, you're able to edit the chart. Now you now go. So the line you want to draw is horizontal line because the vertical axis is the difference. So the mean will be horizontal. The mean of the difference will be horizontal. You are not drawing the vertical one. So you see the icon. There is one that go up. That's not what you are looking for. The one that is horizontal is what you are looking for. Just click. When you double click on it, can you see now? Oh, so I click 2 times. It's first of all, click the mean, the one around the 0, the middle. So let me double click on that one, that first one. Oh, I click 2 times. Let me remove this first one so that, because I don't want you to be confused. Yes, I remove that first one. So this is the one that, as you click, the first click, I want to highlight that line. Sorry. Don't give me. It's because of the way I click on it. Sorry. It has given me. So, so if you look at it now, you will see that line, the first line, he put it on the 0. That is the where the difference is 0. When you are looking for the difference now, you're going to see the axis, you see 0. Let me put the touch so that you can see it. You see 0, anything above will be positive, anything below will be negative. So now, it is only when there is no actually, they are the same. The mean will be 0. So we want to know the mean. So we want to put the mean, is the mean value I want to show. Can you see now the difference between, you now click on set to, is it the mean or median I want to set? No, I want to set to mean, not median. As you set, it gives the value of the mean. Can you see? It gives you the value of the mean straight. Now, you can decide to even work on it. Me, I want to approximate 4.19 something. I will call it 4.2. So that it won't be, because it will show in the graph. I don't want it to be longer. So I promise 4.2. The mean is 4.2. As you now say attach label, you want it to write on it, if you want it to write on it. Because if you don't attach label, it will not write it. Now say attach label, and then apply. Can you see now? If I go, can you see? The two, sorry. How did it move? No. Look at it. As if you can see now 4.2. If you look at it, it's above 0 now. It has moved it to 4.2. That's the mean. Now,
I can see it all.
Okay.
It's not shared. The screen is not shared. The screen of this 4.2.
Okay, but can you see the screen now?
No, it's not shared. It's not shared now.
I can see it now.
Okay, sorry. That showed that the data, the chart editor window was not showing. Okay, I need to share it. I will have shared it. Okay, the next one I will share. So you can see. Can you see now? Because I'm out of it. Can you see now?
Yes, sir.
You see
Yes,
now 4.2. Because the line, when I put the line before, I put it on the 0. But you can edit it. I want it to the line the mean to be the mean. Of course, if it's not 0, it will move it to its position 4.2. The one that is 1.96 standard deviation above the mean. Okay, before we move further, let me run the, so that you can see the mean, how we run the mean. Because I didn't run it before, or you. So that how did I know the mean and the standard deviation? So what I will have done is descriptive. If you are looking at the mean of the difference, so this is the difference. So, sorry, I want to do what do I call it? Frequency. The mean of the difference. Yes, it's descriptive. Can you see the result now? Can you see the result? Descriptive statistic. Can you see? Please, I want you to respond.
Yes, sir. Yes, sir. Yes, sir.
Yeah. Now, can you see the mean? The mean is.
Yes, sir.
No. What is average? I went to click. What's wrong with me? Is average? I went to do instead of. Is the difference we are looking for? It's not the average. The difference. Wait.
It's the mean of the difference, not the average of the average.
Yeah. The mean of the difference. Can you see? That's the last one. Can you see now? Can you see the mean? The mean is 4.19004, and the standard deviation is 25.69. You can approximate 25.7. Can you see now? 25.7, and the mean is 4.19. So that was in the graph. Let me go back to the graph now. We show the graph. If I scroll to where the graph, can you see now? That's why when we inside the mean, can you see it put the mean 4.2? No, 4.19 mean I just approximate to 4.2 here. Now we want to set the limit. The limit of agreement is from minus 1.96 standard deviation to plus 1.96 standard deviation. So the standard deviation now is 25 point. Standard deviation is 25.7. If you multiply 25.7 by 1.9, if you want to use standard deviation, a 2, which is approximately 1.9, is approximately 2. But let's be accurate. Let's multiply 25.7 times 1.96.
So why do you multiply by 1.96?
We are looking for what to set 2 standard or 1.96 standard deviation. 25.7 is 1 standard deviation. Then we want to locate what is 2 standard deviation, what is 1.96 standard deviation. I don't know if you understand me now. Okay, if
yes,
one standard deviation is 25%, what is 2 standard deviation? How will you calculate 2 standard deviation? Please, let's talk, please. This is a workshop. Let's talk.
I'll have to multiply.
Yeah, you multiply. So if you are looking for 1.96 standard deviation, you multiply 25.7, which is the mean, times 1.96, which is the standard deviation, times 1.96. It will give you 50.372, which is 50.4. That's a 50.4. So 50.4 is 1.96 standard deviation. If you now add it to the mean, you know, you can minus this from the mean, or you add. If you remove that from the mean, what does it give you? 50.372 minus 4.2 minus 1 is equal to 46.2 minus 46.2, right?
46.172.
Which is
yes, minus 46.172.
Minus 46.2. Then if it is plus, when you add it, what does it give you? Plus 4. You are adding it. Is
54.572.
Which is 54.6, right?
54.6.
Yeah, thank you. So those are the limit. So when you double click again to go to data editor, I'm there on. I'm sure you are not. Let me reshare now because I've clicked.
Please, we can't see you.
Can you see now?
Okay.
This is the. Can you see it now? So I'm back. No, I'm coming.
We're not seeing the screen yet, though.
You are not seeing the screen?
Please, sir, we can't see it.
Just wait.
Just wait. Let me reshare the screen. Can you see now?
We can see now.
And this is the data here. Okay, before I even. Okay. If you cannot see, let me know. No, sorry, what I was.
It's still coming.
No, can you? Don't worry.
Not yet.
Just wait. It's fluctuating because of. Don't worry. Just wait. Okay. Can you see the screen?
We can't see yet, sir.
Wait too. What's that for? Yeah, I'm sharing now. Can you see it now? Maybe it's just coming. Let me wait. Can you see it? Please, somebody should talk. Can you see?
No, sir. No, sir. Sir, I just spoke. No, we can't see it, sir.
You can't see. Okay, just wait.
The screen is not yet shared though.
Don't worry. When you see, let me know. Can you see?
No, sir.
What do you
Not
see?
yet, though.
Okay, don't worry. Can you see this one now? Can you see this one?
Sorry.
Can you see the screen now?
No, sir.
It's just showing started sharing.
Okay, started sharing.
It hasn't come up yet.
Maybe we should wait.
Because it's the results, even if the expresses I'm sharing, but it's the results window I want us to see. Or maybe it's the rain here. But can somebody share? Who has downloaded that thing? Because it's raining heavily here. Who has downloaded it? Nobody has downloaded it.
Okay, let me share.
Is has not share, right? Can somebody hear me? Can you hear me, please? Hello?
Yeah.
Can you hear me?
I want to share.
No.
Okay, share. Okay,
It's still
share.
loading.
No, I've stopped
It's still
sharing.
loading. Yeah, we
you,
can
sir.
hear you.
Let us share. Let us share.
I can hear
Yes,
you.
sir.
I can hear you.
No problem. Let us
Can
share.
hear you very well, but I think it's your network.
Yes, it's raining
Yes,
heavily. Yes,
please,
it's
we
raining
can
heavily.
hear
Yes.
you.
If the
We
screen
can
is
hear
not
you.
Let
It
Dr.
says you are trying
Igulu
to share
share.
your screen.
Let Dr. Igulu share. Okay, yeah, okay, that's great. Okay. So quickly go to analysis so that we don't waste time.
Sir.
Go to graph, no analysis, graph. It's graph we are in. Graph. Go to graph.
Sorry, something is blocking.
Graph is not it's graph. Graph builder. Click on the graph builder. Or legacy dollar.
Click OK.
Yeah, click OK. Click OK.
Oh, sorry.
Click OK, yeah.
So which one do I pick?
I say
chat builder.
Chat builder. You can use legacy dialog also. The legacy dialog.
Secretary was seeing two different things.
No, you can use
legacy dialogues.
no problem. You can use it also. Okay,
Chat
legacy
builder.
dialog.
Chat
Click
builder.
on scroll to scatter plot. Click on scatter
Click
plot.
on chat builder. After
No, don't worry. You can use legacy dialog also. Go to scatter plot. Even that your own also is slow. Okay. Okay, you now went back to chat builder, no problem. So click on scatter dots. Then the first one, that's drag it to that space that you
think so.
is take it time.
Oh, there's a disconnect between my because I'm already on chat building.
Yes,
and I'm moving the scatter plot.
Don't worry, we've seen it now. Okay. Click on drag the TC average to the to x-axis and different to y-axis. Average to x-axis, you drag it to that x-axis, and the different to y-axis.
average to y-axis, then difference.
No, average average to x-axis different to y-axis. You mix it up.
Average to x-axis.
Average to x-axis, the difference in y-axis.
Okay. Okay. Difference. Okay, so
Yes.
what do I do now?
Yes. Okay. Click OK.
I have to share, sorry.
So share the result, the output. Share the output.
Need to see. Because I didn't share anything.
I'm in a meeting. I will call you back. I'm in a meeting. I will call you back.
It's slow.
Yes, it's showing now. It's coming up. The result is yes. Yeah, scroll down. Scroll down. Let's see it. Let's see it very well.
That's okay.
Yes. Your this thing is version 20 you are using, right? SPSS.
Yeah.
Yes, because if you look at it, my own is version 25.
Look advanced.
Yes, it doesn't matter. So now, for us to edit that graph now, we want to show those like if you look at it now, we have 0 in the middle now. That's the because it's the difference. So you go to have 0, you go to have positive, negative value. Yes, sir.
So which of the files are we using? Is it Blenderman 2 or the one that just without
no, it's not 2. It's the one without 2, one, then the first one without 2.
Okay.
Blenderman, that's the bilirubin, yes. So now you want to now put the line, the mean line, and the 1.96 mean plus 1.96 standard deviation, mean minus 1.96 standard deviation. So we have already know our mean, we know our standard deviation, and the mean will come out. There is the standard deviation, you have to type, calculate what you want and type. Okay, now double click on the graph to go to have you double clicked?
Double click, sir.
But it has not shown. Maybe you have to share that view. Yeah, maybe you can share again.
Yes, sir.
That was the problem I was having the other time. Off and share, you go to see that one is different. It's another view. When you is darker, it's darker. That is the chart editor window. I will go and open the window from the back. I'm hot. Let me open the window. Ayo. Let me open the window from the back. Yeah. So we are not seeing you.
But this is the same. This is what I saw.
No, you don't know what I saw. Okay, don't worry. Stop sharing. That was the problem. I was like, stop sharing. Don't worry. Stop sharing. Just wait. So can you see my screen now, or is it sharing now? Can somebody see my screen?
Yes, better now.
You can see it, right? You can see.
Yeah, we can see it.
That
Yes,
was why we were having problem with shifts. So we have already drawn this line. So let me go back to that when the chart editor. Okay. Check. Can you see if you can see it? Let me know. You can see it, right?
We can see.
Yes, sir.
Okay, thank you. So if you look at it now, you come up, you see I click again, that horizontal line under the the icon. If I click again, it gives me another line up. Can you see? That line up it gave me now. It just set its own value, it just put it a value. there. You don't just accept it like that. So now I want to that value, I want it to be the upper limit. Upper limit. So what did you calculate at the upper limit? You calculate 54.6.
Sorry, sir. Sorry, sir.
Mm-hmm.
I'm sorry to take us back.
Mm-hmm. Go on.
Is the chat editor, where did you click again to bring this dialog box?
No, as I double click, as I click on that line of horizontal, there's something, I don't know, let me point at it. Just wait. Let me touch.
Using your pointer.
Can you see here? This thing, like a graph with horizontal something. That's what I click on again. That was what I clicked on before. It gave me the first line. If you click on it again, it gives you another line up. If you click again, it gives you another line down. If you click again, it gives you another line up. As many you want to bet it, we just need 3 lines. We need the middle one that is our main, the one up and the one down. So you click the one up now, which is we want to set the upper limit with that line. And the upper limit is 54.6. That's the mean plus 1.96 standard deviation. So I will now type, can you see what he give to us? That's the value he give you. The line drawn and the value of the line is 24.42. That's what you want. You want it to be 54.6. As you do it now, you now say attach. If you want it to label it, you are say attach label. If you click, say apply. Immediately, it has moved that line to the position of 54.6. Can you see it? Can everybody see it? Please.
No, not yet.
We haven't seen it yet.
Oh, I thought I was.
Why don't you reshare it?
No, wait. What is wrong with this? Okay, don't worry. Just wait. I thought you. Can you see it now?
No, sir.
Not yet.
Now for this thing. Maybe it's this editor window stuff.
Yeah.
Can you see now?
Not yet.
Okay, don't worry.
It's coming.
Okay.
You can see it, right?
No.
So can you see now? As I put it 54.6, it has moved the line up. If you look at it, it's above 50 now. It's 54.6. That's the upper limit. So if I want to set the lower limit now, I go back to that something, I click again. It gives me another line down. And I would put the value, which is 40 minus 40. Don't worry, let me just put it. Once
your red marker.
What do you say?
I wanted you to use your red, that's your light thing, to just show me where you.
Well, where I click.
Where you are clicking.
This is what I click. Now look at it. This is the same place. This something icon up like a graph with horizontal line. You are trying to say, help me draw horizontal line on the graph. That's what it means. That's what that icon means. Okay. So it has drawn the horizontal line again. They give you, it draw it at around minus 50.8. But that's not what you are setting. You are setting minus 46.2. You now change the value to minus 46.2. So when you do that, you say attach label. You know, when you attach label, you say apply. It has applied. Or can you see it? Or you cannot see and share again?
No, we can see.
Can you see now? Can you see the 3 line now?
Yes.
You can see the 3 line. Yes, the 3 line, they are there on the graph. What this nonsense?
I see it now.
Yeah. Just a minute. So now it's very clear. Can you see? That's the graph I show on the slide. So it gives you, this is the mean 4.2. Then this one is mean plus 1.96 standard deviation. The one down mean minus 1.96 standard deviation. So these limits are the 2 limits of the limit of agreement. It is believed that any value within the two lines, the limit is still in agreement, still okay. But all these values are out, they are not okay. If you do the PIT test, it's significant. It shows that there's a significant difference in the two reading because we have a lot. The graph does not quantify that, but if you do t-test, PIT test to show you, but what the graph is showing you you see the majority is still within. But you will see something. When did you start seeing that the value are going out? Up to 150, anything below 150, we are talking of average bilirubin now. Average the value of 150, anything below it, the line, all the value are within the two agreements. It is immediately after that 150 you begin to see value out. So what it means that when the bilirubin is below 150, the value of total serum bilirubin and transcutaneous bilirubin is the same. It's still the way they are reliable. It's the same. But once the value of bilirubin go up, you see that it's no more. You need to see that we're going to see a lot of value that are different. Is it clear?
Yes, sir. It now makes a lot of sense.
It makes sense here. So you will see.
It is.
We may not bother on it. The other one also is the same thing. That one is potassium. Using blood gas analysis and using electrolyte, blood electrolyte, serum electrolyte. So if you compare the two reading, it shows the same thing. And that was what I was showing you. And the same process. The same process. So let me stop sharing that and go back to my slide. So look at it. Can you see my slide now? So this is what I brought here. So that's how I plotted and brought the result out. So if you look at the other one also is the same thing. If you look at for this one, all the line, all the value they are along within. So it shows that this one show. And if you do the t-test for this one, there's no significant difference. It shows you that both the blood gas analysis to measure potassium and blood electrolyte level, they give the different. So you can say it's reliable. The result coming from both of them, there is agreement. So that's just it. So you see that the agreement is just one way of measuring reliability. It's not all the situation you can use it. I don't know if Prof is listening now. So it's not all the situation you can use the agreement. So it is when you are using two methods. You are using two methods to measure the same thing, and they are quantitative, and they have the same unit. So that is where it is now better. It is believed that it's better to use this one instead of correlation. The reason being that for the fact that something correlates doesn't mean that they agree. For example, now you can even correlate anything that quantitative. You can correlate a score, electrolyte level, and age. Are they on the same scale? Does it mean it is? So when you are even measuring the same thing of the same thing, so you cannot, the correlation will not tell you if they are actually agree. So it's better this one will tell you. But there are situations where you still want to do reliability. Outside this context, you just have to use correlation. Of course, if they agree, it must correlate. But it can correlate without agreeing. Yes, I'm now. So if the result that now they agree now, there will be strong correlation also. But you can have strong correlation without agreement. So that is just a way. It's just like if this is a scenario, then you can use this blunt atma to use it. But when you cannot use blunt atma, you will be left with correlation. I don't know if there's any. So then you can talk about. I've told you about part of the interpretation. Another part of the interpretation is that if let's say, like for this one now, if let's say that one value may be TCV, the TCV, because we may remove TSB from TCB. If TCB is persistently higher, what will happen is that all the value will be above the line, above the zero line. If TCB is persistently lower, all the value will be below the line. Can you see now? Or what can bring the value also, all the value above the line, below the line? A particular method make sure that it will be overestimate higher value and underestimate lower value. Professor Yemi, you are making that from your end. So it may overestimate higher value and underestimate lower value. So I think we just stop there. If there is no question, so that we'll move to the business. Is that okay? Is that okay? Any question? It's very clear. Okay. Now we're going to start from where we were yesterday. So what we first of all did yesterday was yes, we were talking of a reference. So somebody was saying that I had to repeat. Is it to repeat the explanation or the running? Because we ran it yesterday. Is it to run it again or the explanation? So what was the problem? Because people were tired by that time. What was the problem? Please, people should respond quickly.
Explanation.
Hmm? What was the problem of yesterday concerning the reference?
There was explanation.
Explanation of what? Explanation of which one? Okay. What we talk about
was
is
this reference interval.
Okay, let's quickly, within 10 minutes, let's quickly do that because why I presented that yesterday for
I'm
us.
thinking that
yes.
maybe we run it to make to be clearer.
Okay, we'll run it, but okay, let's just run it. So any other place you can come back and make it. Okay, will somebody run for us? Or I should still run. Will somebody run it for us? Somebody share?
So which data?
The data is reference interval. Are you sharing? Or maybe I should do that now. That was time. Okay, let me do that. Let me do that. So this is the data. This is the data. Can we see? Can we see? Please, when I ask questions, I want somebody to read. At least I need one person. Yes. Protein, serum protein, PCV, and alkaline phosphatase for neonates. And there are 119 neonates we took the blood sample from. So we want to, let's say we want to establish reference interval for the neonate. Let's say for the neonate. Now, so you can see why it's good to do. Sometimes the level of all these electrolytes may be different and the protein may be different from in neonate than adult. Sometimes we use one blanket. This is the normal level and we use it for our children. So sometimes it's good to do our own reference, in the laboratory to have reference for different age group. Even sometimes sex, it varies with sex. Some things vary with sex. So now, the first thing you want to do, we talk about two methods. So we talk about, we can even run both together. We talk about the normal distribution method and what do I call it? The percentile, non-parametric percentile method. You may want to, okay, should we even check for normality to see? Should we explore these three variables? If we want to explore this to really see if they are even, if they are skewed or not, we can even, let's explore. We go to descriptive and go to explore. Under the explore, just move them because they are. So the three of them want to explore and plot histogram with stem and leaf. So I think that will be okay. So let me share the output. Can you see the output? So for the first one, let us go to histogram plot. Look at this is a protein. Look at it. Look at this shape now. So it's skewed to the right.
Yes,
so if you look at the value of the mean, if you look at the mean, the mean is 6.3. Is this that somebody
Okay.
cannot see? Is this that somebody is talking? Everybody can see, right? So the
Yes,
mean
sir.
Yes.
6.3, the
6.3.
median is 6.3, but the mean is 6.315. The median is 6.3. So it's just slightly skewed. But we cannot say so because you know the unit is very small. So something that is 6, 0.15 is a big thing. Something that the mean is 3, 0. But if the mean, let's say you are talking of figure, big figure, 70, maybe say 0.15 may be a small thing. So you can still see that the mean is greater than the median. It shows that it's skewed to the right. If you look at the PCV, the mean is 46.7, the median is 47. Can you see? It's skewed to the left. Because the mean is smaller than the median. If you look at the alkaline phosphatase, the mean is 53.01 and the median is 52. So this one is skewed to the right also. Now, if we look and check their shape, this one we know that it's skewed to the right. No, this one is skewed to the right. This is the first one now. This is the protein. This protein is skewed to the right. The other one is skewed to the, I think this one is PCV. But this one, look at, but it's showing that it was skewed to the, I thought the median was bigger than the mean. Okay, well, let's see, it's skewed to the, it was shown that it's skewed to the left. Well,
Okay.
yes, you look at it, you see, that's the, look at it, you know that it's skewed to the left now. Look at, because look at the, you can also know, if you are confused by the histogram, you can use the box plot. Because if it's normal, it will be in the middle. If it's skewed to the right, the upper part will be bigger, but it's skewed to the left, the lower part is bigger. Can you see now? And if you compare it with the protein, can you see? Well, what is it showing?
Wait, so you said it's skewed. No, I didn't get, because the median is up.
No, we are talking of the spaces. The spaces. Okay, the value just, okay, let's just use the value, don't just wait. But this one is clear that this one is even skewed to the right. Can we see?
Yeah, this one is clear.
It's skewed to the right. Yes, I just want us to have a flair about it, but don't worry. Let's just go back to running it. Let's run it. You see, the reason I said something yesterday that the International Federation of Clinical Chemistry recommend the non-parametric percentile method. You will see the reason they do that. Okay, let's say analyze. Let's do descriptive. So let's move them. So I want to show mean and standard deviation also, yeah? Mean and standard deviation. What did you say? You cannot see?
No, I can see.
Yes.
I can see.
I thought you were saying something. Okay. So what I did here is to put the frequency also under the frequency also. You can also run the frequency, also show the mean and standard deviation. So
Okay.
yes, that's what I did. Let me share the output. You may not be seeing it. So can you see the output now? Look at the protein. Okay. The output is supposed to first of all show me. Let me first of all even clear those. You know, sometimes it's good to clear. Let me rerun it. Let me clear it and run it. I don't like it. Sometimes when you have too many things there in your output, you'll be scrolling, you'll be looking for what you have done. I don't prefer clearing it, deleting it, and run it again so that you can see the output now. So look at the first table. The first table is the one showing their mean and standard deviation. Can you see? Can everybody see? So protein, PCV, phosphatase.
Yes,
Look at the mean. The mean of this one, 6.315. Standard deviation, 0.7643. Then the mean for this one, 46.74. Standard deviation, 5.384. The mean for this one, 53.01. Standard deviation, 80.60. So you have to note all these things because the computer, the remaining thing, the computer is not doing it for you. apart from giving you the mean and standard deviation. So you have to now note them because it's you that will now want to set the lower limit will be the mean minus 1.96 standard deviation multiplied by standard deviation. Then the other one, the mean plus 1.96 standard deviation. That's why you must note the mean and the standard deviation, which you saw on the table before. I don't know if you follow what I'm saying. Now, how do you do that? Is how to for normal distribution method. Then for non-parametric method, you know you are run the frequency. Can you see from beginning to end? You see it show you cumulative frequency. That's the cumulative frequency. Can you see now? Cumulative, it will be adding it. So if you look at it now, the first, and you want to, you are looking at both sides because the attribute you are looking at, protein, alkaline phosphate, you are using two-sided because it can be low, it can be high. So now you are looking at what are the values that correspond with 2.5% up and down. So the 2.5% down, the first 2.5% is 2.5% there. The last one will be coincide with 97.5. So if you look at it, even the value we see here, 6, this value 6 that is here is 5%. It's telling you it's 5% of the whole data set. So that shows that the 2.5% is 5 also, is 6 also. I don't know if you remember. So the lower limit for this one will be 6, and the upper limit will go down. Which value coincide with 97.5? 97.5 will be, look at C. This one we have 95.8 here. We have 98.3. So the value is 8 because the 97.5 percentile will be 8. So it is for this one 6 to 8. Is it clear?
Yes, sir. How did you decide on the percentiles?
The percentile is just what it does is it arranges it according to percent, divided into 100. It gives you the percentage of each one. And the percentage of each value is put under, when we discuss, those are the things. Statistics, whatever you learn from the rudimentary, you use it at any stage. If you remember when we discuss a basic concept of statistics, we talk about distribution. So we talk about the pattern of occurrence of the value of variable in a data set. And this distribution, we have different 4 types. We have frequency distribution, which is the real number, which is the frequency, the first column after the value. Then we have the relative frequency distribution, which is the one that is expressed in the percentage. We also have cumulative frequency distribution, though they didn't put that cumulative here. The cumulative here is that it will be adding each of them, but what they put here that is useful is the relative cumulative frequency, which is the percentage. You are adding the percentage. This is the percentage for each one here now. Then as you are going, you are adding one by one. So here now, 5, this number 5, the value 5 is 5%. Value 5.2 is 7.6 is 2.5%. But you add it to that 5% to make 7.6%. Value 5.4 is 4.2%. But you add it to that 7.6 to make 11. So it will be going. So that is why it is easy for us to just look at it. Okay, the first 2.5%. Where does the number 2.5 percentile should be 5? One of those 5. So then if you go the 97.5. So you see 95.8 here. You also see 98. That shows that is this one that is 8 that has that covered and moved from 95.8 to 98.5. So the lower limit is 5 and the 6, the value is 6 and the upper limit is 8. So is it clear now? Is it clear? Please respond.
It is.
Like I was just trying to, I understand this concept, but I'm trying to understand how you got the range. Are you just looking for the minimum and the maximum value?
You are looking for, that is okay. Now, let me just share the slide. You see, we discussed that yesterday. Why is this thing freezing? Oh my God. Yes. Look at this. Look at this. The non-parametric method, the percentile method. If we are looking at, if both of them is looking at the other one, this one is looking at minus the normal distribution method. Is looking for from minus 1.196 standard deviation to plus 1.9 standard deviation. We have done that one. This one is looking at the from
Oh, I get you.
2.5 to the extreme. We are looking at the middle 95%. So the middle 95%, you have excluded anything that fall outside the something is not normal. The normal range will be between 2.5 to 97.5. So the remaining initial 2.5 and initial the later 2.5 make up 5. That will be the 5% outside. That's what it is. So it's very simple.
Yeah.
So that is you
I
just go.
understand. Sorry, I forgot. Yeah.
Yes. So you can see it now. So that is how we got it here. Then if you now go to PCV 2.5, you see the one that give you 2.5 is from 38. Can you see from 38? Can you see? Because if you look at the cumulative frequency now, this is 5% here. This one is 1.7. So is between 1.7 and what move to, so you can find is 38 that will capture the first 2.5%. 38. If you now go to 75, can you see this is 90? This is 96.6, 99. So it's 60. So between the range is between 38 and 60. And this one, you look at it, 2.5. Can you see the first 2.5? But you know the range. So what you are capturing is 25 here, because this one I give you the anything after this 2.5 is what you are actually looking for. So this one will be from 25 to this one is 97.5 or 101. Or if you capture well, if you can just put 2 point, well, you can put the point 2.5, 24 to 97.5, 98. And that was how we got the let me go back to that slide because everything. Yeah, yes, reference, yes, I put on the slide there.
I don't know whether I can ask a question.
You can ask, sir.
When the values are not clear,
Your this is freezing. Your voice.
If you are looking at the 95th one and it's not available, there is 96. Some type of 95%, the 95th percentile.
No. So what you are looking for is actually 22.5 percentile and 97.5 percentile. That's what you are looking for.
Okay, if we are looking for 97.5 percentile, and if there is no specific value,
yeah,
is there any maneuver like finding the average?
So you now move, if there is no specific value, you now move above it, the one that is more than it, any value that is there is that value that has captured it. Let me just demonstrate it now. It's not a big deal. Look at it. Look at that first one we did. You see 95.8 here. Let me put the touch. This is 95.8. You know that it's not up to what you are looking for. But when you come here in 98.3, it's more than what you are looking for. But of course, that shows that value, because 95.8, the value is 7.9. So we now have some 8. For the 8 we have 3 of them. It's one of them that will contribute to reach that 97.5. It's because there are plenty. We have 3 of them that are 8. That's why it gives you 98. So that value that coincides with 97.5 is this 8. Does it make sense now? Yeah. It's the same thing. Yeah, it's the same thing here. If you look at it, you can't see 2.5, but there's 5. It means that that's 5. The value that is 6 here is the one, because I say 6 is 5 rather. The 5, the 5 that is the value that is 5. Welcome. The 5 that is 5 here is the one that there are 6 of them. Is the one that moved from 0, from 1% to 5%. So it is there you capture 2.5. That is why 5 is the value we pick there. Is it clear now?
It's clear.
Yes.
So that's that one. Okay, I think we just move to so can you see? That's what I show here. Is what we just analyzed now. I put on the table here. What we just analyzed now. I will just see here. So you see, for the non-parametric method, you can see the range. And the other one, what I now did is that to put the standard deviation here. And actually, what I calculated is it 2 or I think it was 1.96. I said I wanted to correct it yesterday. It was 1.96 that I actually used. 0.96. I used to calculate it. So standard deviation, you got it. So when you remove the 1.96 standard deviation from the mean, it gives you the lower value. If you add it, it gives you the higher value. I see now. So you will see something that just 1 minute. So you will see that when you look at it, if you remember when we did the what is making noise? So when we explore, who is making noise? When we explore, you see that the one that is close, almost normally distributed, that is least crew, was the serum protein. If you look at it now, the range with normal Gaussian method and non-parametric percentile method, although they are close, 4.6 to 7.7, 5 to 8. Can you see? Very close. The differences you see are in this one 35 point, let's say approximately 36 to 58, and this is close, still close also. This is 38 to 59, but the one, if you look at the one that was most skilled among them, is this alkaline phosphatase, 15 to 19.1, 90.9, and here is 24 to 98. So you will see that if that thing is normally distributed, the value with normal distribution method and non-parametric percentile method will be very close, if not the same. But if there's skewness, the value will be different. So because you know that if something is not normally distributed, you cannot apply the normal distribution to it. So it's better you use the non-parametric percentile. But if it's normally distributed, even the non-parametric percentile method and the normal distribution method, they give you the same answer. And that is why the International Federation of Clinical Chemistry and the clinical medicine, clinical chemistry, yes, clinical chemistry now say okay, and laboratory medicine, and now say okay, they recommend the non-parametric percentile method for doing normal rate. I think it's very clear. Any question so that we'll move forward? Is it clear? Any question?
Yes.
Very clear, sir. Thank you.
Okay. Okay. Now let's move to this business proper.
I think somebody had a question. No.
Okay, who has a question? Okay. Is it that the person chat, no chat? Who has a question? Somebody raise hand. The person should ask the question. The person should ask the question now.
No,
Yes,
I was,
go ahead. Now there's no question now.
I was the
Okay,
last
because-
person who asked the question. Answer.
Yeah. Okay, that's fine. Okay. Let's proceed. Yes, we want to look at the criterion validity of diagnostic tests. So what we have just done now is to look at reference value, what the, okay, if you take sample from apparently normal population, what is the range of value? So that outside that you may be considered, you don't actually use that one for diagnosis. Because even those people, the few that have extreme value, they are not sick also. They may not be sick. If they do your this thing, and it may look as if it's high or low, extremely high or low. You may be one of those people that you have the extreme value. But if somebody now come under treatment, maybe you are trying to make decision about the person's treatment. If you do the test, it may not guide you that, oh, now this thing is outside this range. So let's see, because it's possible this one may be contributing to the sickness or it's a manifestation. Therefore, the person that doesn't have complaint, you do the test, it doesn't really mean that you have to go and search the people that have that low value and say you want to treat them. No. But whenever people now sick, you want to make diagnosis, how do you take decision of people that have the disease or not? That's another thing. And that is where this criterion validity of diagnosis test. You know that validity is a way of knowing the degree to which the test say, okay, probe what is supposed to probe. So if you want to diagnose, a diagnosis test should be able to tell me if somebody has the disease and say you have the disease. If somebody does not have the disease, you don't have the disease. That is what the diagnosis test should give us. So in validating diagnosis test now, you know, it's a form of criterion validity in the sense that there's a criterion. You have a test, but there must be something that will help you know that, oh, this person have the disease also. So most of the time, you have a gold standard that will help you know that this person has the disease. Most of the time you have, but not all the time you have also. But there's a way people play around it. Like for some now, we know that pathology will come up with a biopsy, do something to tell that this is confirmation that this person has it. Most of the time, biopsy will tell us if the person has the disease. Sometimes also, by the time you have done all the examination and some other tests, and you need to see some complication like diabetic now, you now can put this person has diabetes. So now, there are some of these tests that they are the most important for it, like for diabetic now. The most important is the blood sugar for diagnosis, fasting blood sugar. Now, how do we know which value, at which value we say that this person has diabetes, I want to be treating this person? Somebody is making noise in the background. I don't know we are recording this thing. Please, everybody should move. So, Dr. Kobo. Okay. Now, for every diagnostic procedure, there's a set of fundamental questions that will be asked. And those are the things I've been saying before. If disease is present, what is the probability that the test result will be positive? That is, if somebody has the disease, what is the probability that a person that has the disease, the test will pick it and say you have the disease? That is the sensitivity of the test. So by the time we move on, I'm going to see the mathematical aspect of it. If the disease is absent, what is the probability that the test result will be negative? That is, the test result will say you don't have the disease. If the disease is absent. No, most of the time, it's only God that knows this thing. Now, that will be the specificity. Then, if the test that is looking at it from the angle of if the disease is there, if the disease is not there, what will the test tell us? Now, let's look at the test. Let's put for the test first. If the test result is positive, what is the probability that the person has the disease? Can you see now? Because it's not the people that the test is positive that they have the disease. And if the test is negative, what's the probability that the person does not have the disease? That one is the negative predictive value. The first one is the positive predictive value. Why you as clinician, you are interested in the sensitivity and specificity of the test because you are looking for this test. I want to help me to capture those who have the disease and say they have. Help me to capture those who don't have the disease so that I know who to treat and not to treat. But your patient is not, that one is not the headache of your patient. Your patient, their own problem is the positive predictive value and negative predictive value, even though they may not know what it means. But that is their interest. For example, now, somebody will come with, most of you will have experienced it, where some of your relatives, they come to see you in the hospital, or some of the friends. You are not the one treating them that day. You are not even the one, it's not in your video, but because they know you. You know somebody in loot? Yes. And I say, he has collected his result. It's possible they have even explained. Because he's not familiar with those people. He's looking for somebody that can have the empathy. I know. And I'll be waiting for you. Say, I'm in the clinic. I say, I will wait. I'm waiting for you. By the time you finish, and I say, doctor, I have done the test. This is the result. Now, it's positive. HIV is positive. Hey, they have told me, they now ask you, doctor, from your experience, if a test is positive like this, does it mean that I have HIV? Or what is the probability that that person has HIV? So I'm telling young people, especially education people, will ask you, they will tell you what is the probability, what is the chance that if somebody has positive result like that, what's the chance that the person has the disease? They will ask you. It's asking you positive predictive value. Or if something is negative, they say that doesn't mean I don't have the disease. So we move further. You will see that all those things. So when you want to actually take this decision we just explained about, or analyze the result like that, you see that there must be, you have a test. You that you are interested in this test, fasting blood sugar, how good it is to separate people that have disease from people that don't have. Or maybe it may be cervical cancer through pap smear or through many other procedures. So most of the gold standard, I will tell you, because we say that, look at the statement here. If somebody has the disease, how do you know if the disease is present now? So the test will give you results, but you are not so sure if that test is telling you the right thing. But how do you know the right thing? That right thing, who has the disease? Most of the time, you have a method that is a gold standard. So sometimes when you are trying to validate a tool, like somebody here now, Dr. Iraq, you are validating it. You are validating a tool, a method for diagnosis. You must have, maybe there's another method that is more difficult, that which it has been established that it is true. You will use that one as a gold standard. But this method, you are trying to validate, maybe it's cheaper, it's less risky. You want to see how close, because if it's not good enough, even if it is not risky, it's cheap, it's not good to use it. But something can be cheap, practicable, and it's still valid. It's still doing the same thing as the one that is invasive and is more difficult and costly and more risky. It's doing. So that is what you want to do. So you now put your own test against a gold standard. Now, this one is just giving you a mental picture of how it works. When you have in the population, you will see that there are two groups of people. It's, based as, okay, we are talking of disease and non-disease now. as a doctor now, as a physician, that's where you see the whole population, sick and not sick. And that's why when somebody call, you want to know if the person is one of the sick you will need to treat, or somebody that does not need treatment. So by a particular disease now, there are two group of people. So there are two populations. The population without the disease and the population with the disease. So, and both of them, the test result, look at the horizontal aspect of this graph, is the test result, the value the test result will give us. The vertical is the frequency. Now, you will see, well, this one is assumption that the test result, as the test result increases in value, the disease increases. There are some situations where as the test result is smaller, the disease is more. Like anemia now. The more the result is small, the smaller the result, the more anemia. So it has to be on the other way around. You have to put the disease graph will be before the without the disease graph. But in most cases, like issue of diabetes, issue of hypertension, and many other things, that as the value increases, the disease is there. You will see that the graph of the disease population will be on the right side. The graph of the normal one will be on the left side. You will see now, without the disease now, of course, in the population, most of the people are not sick. So, can you see the graph? It's a bigger graph with higher frequency, go up and down. The test is also will be normally distributed most of the time, especially even if the normal one, they nearly normally distributed. For the people that are diseased, they have the disease also, the test result will be like that. But it's a smaller population. Now you will see something. There's an overlap. There's an overlap between the test result of normal people and people with the disease. What it's telling you is that there are some people that have extremely high value of the test result, they are not sick. They don't have the disease. And there are some people that have some lowest, relatively lower value of the result, but they have the disease. There are many factors that may be responsible. Some people have the disease, is on treatment. So the value of the result may be lower than it will have been, but it doesn't preclude the fact that he has the disease. Like a diabetic that is on treatment doesn't mean that the person is not diabetic. So you see overlap now. Now, when you now do your results, any of these people can come to you complaining of headache of whatever. You do the test, you want to know if they have that particular disease or not. So you have overlap of two populations. We don't know which one anyone belong to. So at what level will you now set any value above this level? You are going to treat. So look at what I put. I said the red line. I also put some vertical line. The dotted line. So you can put your value in any of these three. The red, dotted, and green line represent possible cutoff value that will be used to classify subject based on the result. You can use any of them. Then what are the implications of using? So I ask a question here. What would be the advantages of selecting the red line and the cutoff value for normal? Sorry, can you see? So if somebody selects red line now, what will happen? What's the advantage? The advantage is that if you look at it, that's the beginning of the graph for the diseased people. So if you select the red line, you can be sure that everybody that has the disease, that you have marked them, they have the disease. Because that's the beginning of the disease graph. If you choose red line at the cutoff value here, so if you are moving along the test and that's it, this value here will be the cutoff. You can be sure that nobody that have the disease escape your diagnosis. If they come, you'll be able to get them and see they have the disease. But what is the advantage of choosing green line? The advantage is because the green line, anything below you say they don't have the disease, anything above. So you have excluded. The advantage of seeing green line is that you are excluded everybody that is normal. You will never capture them and say they have the disease. But what are the disadvantages? Because those are all the questions I asked here. What would be the disadvantage of selecting red line? Disadvantage, if you know the advantage is that you have captured everybody that have the disease. But the disadvantage is that you have captured some people also. In fact, look at the people that they don't have disease. You are marking them that they have the disease also. They don't have the disease, but you have captured them. What is the disadvantage of choosing green line? No, we have already talked about the advantage of green line. The advantage is that you have excluded people that don't have the disease. But the disadvantage is that a lot of people have the disease also, you have excluded. Now, you now have to reach a compromise. The compromise will now be this dotted line. That way, you set it, it will capture. You look at that dotted line, at least it captures many, more than half of the people that have the disease. There is also included some few people that are normal that they have the disease. Now, you know, we said these are two populations, the normal and the people that don't have disease and people that have it. But now, by your decision of using this dotted line to have your cutoff, you actually divide into T4. The people that have the disease, that you have marked to the right that they have the disease, that will be your true positive. Because by this cutoff here, the people that have the disease, really, and your test say they have, by your reason of your cutoff, they are the true positive. But there are some people that they are normal people you have captured with them, which is the false positive. All of them, they have anything after this dotted line is positive from your result. They are divided into true positive, people that really have it, and false positive, people that don't actually have the disease you are capturing. Then, that dotted line, anything below the left of dotted line, they are negative, you have to term them. Any value below that line, below, on the left side, they are negative result. But there are people that don't have the disease. If you look at true negative, they are a normal population, true negative. Yeah, those are the true negative. But there are some people that have disease, you have captured with them, they are the false negative. I don't know if there's any question before we proceed, because that one is just to create a mental picture of what we have here. Any question? So these are the questions I just answered, and I've answered them. What would be the advantage of selecting red line as the cutoff? All patients with disease will have a positive test result, but the advantage is that patients who do not have disease will be classified as having the abnormality. Well, what is for the green line? What will be the advantage of selecting green line? All healthy patients will be in the test result, negative result, you excluded. But the disadvantage is that the person with disease may not be diagnosed. I've explained them. I don't know if there's any question. Now, if there's no question, if there's any question, you can let me know. If there's no question, still to explain further. What I just explained now, you can now put in the table and still come and extrapolate. You can now know that whenever you now put the same thing, your test on 2x2 contingency table, the vertical, though some you see some people, they still put along the horizontal as the true the disease, which is that it can be confusing. But the convention, the best is to put it, the people that have the disease, that is, which is represented by the gold standard, will be the vertical. While your test result will be along the horizontal. So look at this one, test, positive, negative, along the horizontal. The disease, defined by the gold standard, present, absent, along the vertical. You will see this first, the A, which is the true positive, are the people that actually have the disease, and the test said they have the disease. D, which is true negative, are people that don't have the disease absent, the test said they are negative. But we have the two discordant. That's why I put them in the Right. The B, false positive. This person, the disease is absent, but the test say is positive. False positive. And false negative, the disease is present, but the test say is negative. Now, the true positive, if you look at, okay, among those people, if you look at when we define, I was explaining sensitivity, specificity, positive predictive value, negative predictive value. When you wanted to explain sensitivity and specificity, the denominator would be among those people that have the disease, among those people that don't have the disease. Can you see? So you are using the vertical total as your denominator when you want to explain your sensitivity and specificity. Because it's the same cell you use to explain sensitivity and positive predictive value, and the same cell for specificity and negative predictive value. But what differs is what you use as denominator. So if you want to explain sensitivity and specificity now, we are using among those who really have the disease or among those who don't have the disease. If you look at it now, the people that have the disease, they are A plus C. That's the total vertical. The people that don't have the disease, they are B plus D. Then if you now want to look at the people that have positive tests, they are along the total, along the horizontal. The people that have negative tests, total along the vertical. So this horizontal and vertical total, they are denominator for positive and negative predictive value. While the total along the vertical are the denominator for sensitivity and specificity. So sensitivity is among the people that have the disease, which is A plus C. How many the test say is positive? That is A. That is why it is A over A plus C. You express it as percentage. Is the degree to which your test is able to capture the people that have disease and say they are disease. That is, if you can capture as many like that, they say, that test is very sensitive because it's able to pick many people that have the disease and say they have it. Now, if you now look at the people that don't actually have the disease, defined by the gold standard, how many the test say they don't have? That will be specificity. Say this disease is specific. It didn't touch people that don't have the disease. Can you see that? If the disease is high in the test, sorry, the test is specific rather, not the test high specificity. That is, it didn't touch people that don't have the disease. So it's able to say most of the people that don't have the disease, they don't have it. It's specific. Now, I think you understand sensitivity and specificity now. And that is what the clinician is interested in, because the test is for you to make decision. But the other side, the predictive value, when you look at the total for positive now, positive test, out of these people that have positive test, how many of them actually have the disease? The total that have positive test, they are A plus B, and the people that actually have the disease are A. Just a minute. Hello? Hello? Hold on, please. Come and give it to your mommy. Hold on. So the A all over A plus B, that is the positive predictive value, while D all over C plus D, negative predictive. That is, negative predictive value means among the people that the test said negative, what is the probability that actually the person doesn't have the disease? Because that's what the client is interested in. They will carry test to you. Say, now that you say it's negative, what does it mean? Do I have it or don't have it? Or when now that the test is positive, what does it mean? Now you will see that, as I've said before, that the cell A total 2 positive and D 2 negative. They are the set to calculate both specificity, sensitivity, positive value and negative value. Because A true positive is the set for calculating sensitivity and positive value. But the only difference is their denominator. The denominator for sensitivity is A plus C. For positive value, the denominator is A plus B. While set D, which is true negative, is the set for calculating specificity and negative predictive value. The only difference is the denominator. The denominator for the specificity is B plus D, while the one for negative predictive value is C plus D. Now, the prevalence of the disease, what is the, what defines the disease is the gold standard. So the prevalence of the disease will be this A plus C, because that's the total for the people that have the disease over everything, which is A plus B plus C plus D. The prevalence of the disease is the practical year over the total, which is A plus B over everything. Then some people define the accuracy of the test. How accurate is the test? That is, some people call it extent of correct classification. The correct classification, we know it now, is the A and D now, is the true positive and true negative. Everything that is false is not correct. So A plus D, that is true positive plus true negative over the total. That is the accuracy. And separately on their own, the specificity and where you validating the test, positivity, sensitivity, and specificity. They are measure of validity. They are the measure of validity, but on their own separately. But adding them together, that is the measure of accuracy of the classification. I don't know if there's any comment or any question before we proceed, because the diagram before, I want to, though it's the same diagram I explained there, I want to bring something out from here. Is there any question? Is this clear, right? We move on. Now, if you look at this diagram here, it is the same thing I said the other time. When you put this cutoff point, so it will give you total positive, true positive, false positive on this side, then true negative, false negative. Now, which one add up if you want to, because this table now, why I put it under this table, so I want to explain in conjunction with this table. Sorry. If you want to say total, now you know we have total from both sides now. We have total vertically, we have total. Which horizontally, which total do you add up to 100%? If let's say you want to calculate that, you want to add something up to 100, which total? If you look at it critically, if you look at this graph, which one defines the healthy population? The healthy population here is made up of the true negative and false positive. Can you see now? Those one true negative, that because that's what we have, can happen to any people that's healthy. Any people that are healthy, they give you test. The other give you say you don't have the disease, or they say you have the disease. And when they say you don't have the disease, if you are healthy, it's true negative. When they say you have the disease, that's a false positive. If you look at it on the table here, true negative and false positive, they are bad along the vertical. Because they have been absent. People that don't healthy people, they are absent, disease absent. B plus D. But if you come to the people that are present vertical here, you will see true positive and false negative. The people that have the disease, two things can happen to you, the person that have the disease. They give the test, they say, oh, it's positive or it's negative. When they say it's positive, that's a true positive because the person has the disease. If they say it's negative, it's false negative because the person has the disease. So if you look at it, the true positive and false negative are the one that add up to 100% here. So having said that, okay, the slide that, oh my God. Okay, let me just skip these two slides. Because what I just explained now, there's a slide Yes, let me just quickly explain this slide so that I won't forget that thing before I go back to the other one. Because of that, what I just said, because of that, on this table, okay, maybe that was the reason I even brought this table, but it's okay. Because of that, on this table now, you can now say sensitivity. You know the sensitivity is true positive. Right? If you are using vertical now, we have already pinned our mind that we are using the vertical summation. So sensitivity true positive, which is A all over A plus C, plus false negative. Can you see? That is, these people, this column, they have the disease. It's whether that you say the person has disease, that's the sensitivity, or the person doesn't have, that's false negative. They add up to 100. So they add up the total for the people that have the disease. That is equal to 1. Now when we say 1 on 100, it's the same thing. So if you say 1, you express your sensitivity of false negative rate as point something. If you say 100, you express as percentage. So 1 and 100 is the same. So you can now say that sensitivity is 1 minus false negative rate, or false negative rate is 1 minus sensitivity. So any of them surface. The same thing with this one here. Because the population that are normal, no disease, is specificity true negative over B plus D plus false positive. They are the one that make up the total here. So you can well say specificity is equal to 1 minus false positive rate, or false positive rate is 1 minus specificity. It's a useful mnemonics. You can call, okay, if you want to say sensitivity plus negative. Can you see? Sensitivity negative, that is sensitivity false negative. Specificity true positive. So PP, specificity positive, that is specificity plus true positive, make up 1, while sensitivity and false negative make up 1 also. So we'll come back there. So let me now, there's something here that is very, very interesting. Because I have explained before that that predictive value is what the patient, your client is interested in. They're not interested in your sensitivity and your specificity, because if they are interested, they will not even come to you, because if that's their interest, they will have treated themselves, take the decision. But it's you that you are making diagnosis. That's why they come to you. You are the one that can make diagnosis and treat. That's why they come to you. That's your own ethic, sensitivity and specificity. But the predictive value is their own headache. They will eventually become your own headache also, because they will still come and ask you. But that's what they are interested in. Now, the effect of disease prevalence on the predictive value. We have 3 scenarios. Please, if there's any question before we move ahead, though, because I'm talking about another thing now. I want to iron this out before we continue to how we do cutoff. Because if you don't understand those fundamental issues, to interpret the result, when you reach to where you do your cutoff and all those stuff, it becomes, there's nothing mysterious about it. Just precept by precept. Once you understand it, very simple. So there are 3 scenarios here, and these scenarios are put on the table. On 3 tables, rather, on tables. It's showing you 3 scenarios with 3 different disease prevalence. Look at this first one. The people that have the disease are 100, and people that don't have are 100, so the total is 200. And 68 positive result among the people that have disease, 32 positive result, and negative result. There are more people that don't have disease, 2 have positive result, 98 don't have, they have negative result. Prevalence of the disease will be 100 over 200, which is 0.5, which is 50%. It's a little bit higher. Now, sensitivity is 68 over 100, that is 68%. Specificity is 98 over 100, which is 98%. The positive predictive value will be 68 over 70. You know, I've already told you that it's the same value you use to these two sets that the one you use to do the denominator has changed. So sensitivity is 68 over 100, but the positive predictive value is 60 over 70. 60 over 70, which is 97.1%. Negative predictive value 98 over 130, which is 75.4%. When you now move to this second scenario, you see that the people that have the disease 100 still, but the people that don't have the disease 1,000. So the total is 1,100. The prevalence will be 100 over 1,100, which is 9%. Can you see? 9%. The disease is extremely low compared with the first one, which is 50%. But the sensitivity is still the same because 68 over 100, and which is 68%, and specificity is 980 over 1,000, which is 98, still 98%. So both sensitivity and sensitivity, they are still the same. But look at the positive predictive value, 68 over 88, which is 77.3. Before it was 97.3, it has dropped. Now, the negative predictive value is 980 over 1,012, which is 96.8. Before it's 75.4, but it has risen up. Now, let's look at the third scenario. The people that still have this, they are still 100. But the people that don't have is 10,000. Total is 10,100. The prevalence is 100 over 10,100, which is 1%. Now, the sensitivity is 60 over 100, 68%. Specificity is 9,800 over 10,000, which is 98% still has not changed. The positive predictive value is 68 over 268, which is 25.54%. That dropped again. If before it was 97.1, it dropped to 77.3, now dropped to 25.4. The negative predictive value is 9,800 over 9,832, is 99.7. It has risen. It was 75.4 before. It rose to 96.8. Now rose to 99.7. Now, what can you deduce from this scenario? Okay, maybe I should allow people to talk because the thing is sounding monotone. I asked you to ask question, you are not asking. Is there any who can deduce anything from this? Maybe one or two people. Are you with me at all? You have to unmute yourself.
Yeah.
We are.
Yes, sir.
So who can deduce anything from what we have just explained here?
The sensitivity and the specificity remain the same.
Yeah, okay.
Irrespective of prevalence.
Yes.
But as the prevalence reduces, the positive predictive value decreases, while the negative predictive value increases. Almost 100% for a very rare disease.
Okay, that's great, sir. So, any other person want to add something to that? Okay, so let's continue. Now, let me explain. Yes, what Prof said, correct. You will see that sensitivity and specificity yield consistent result for the diagnostic test in a variety of patients with different disease prevalence. Even if the disease is different, the test, because it's a test, sensitivity and specificity, they are characteristic of the test. They are characteristic of that test. So, like for HIV now, that the prevalence consistently, Osun State have been having the lowest prevalence of HIV in Nigeria, and state like Cross River, Rivers or Benue sometimes have the highest prevalence in different occasions. Do the test, HIV test, in Osun, in Kano, in Cross River, in River, in Benue, any Nondo, anywhere, with different prevalence of HIV, the sensitivity and specificity of that particular method will remain the same. So the sensitivity of that test, because it's a function of how many people have the disease that come and what proportion the test is able to pick as having it, and what the proportion, the people that don't have, what proportion the test say they don't have. It's constant, irrespective of the prevalence of the disease. However, the predictive value, which is the interest of your patient, they vary with the prevalence. So that is why when the prevalence of the disease is low, even a highly sensitive test will have low predictive value. The implication of that is that if you are in maybe river where HIV prevalence is a little bit higher than Osun, if you present a positive test and you go to do test, they say it's positive, and somebody in Osun also go to clinic in Osun and they say it's positive, the probability that the person that have the positive result in river being actually having it is higher than that of Osun. So that shows that since the prevalence of disease is low in Osun, when they present you with, you say you have HIV, the probability that you have HIV is slimmer. You may not actually have it. It's similar than if, let's say, you are in another population where the prevalence is low. Does it make sense now? So it has implication. So if you are in an environment where the prevalence of that disease is low, and the person just have it, so you have to, that is why when you do screening, you don't take her to another dimension. When you do screening, you have to do confirmation, because you cannot just rush because somebody has positive result, especially if that environment is an environment where that privilege, that thing is not common. The other way around also, the negative predictive value. If somebody in Cross River now brought to you that they say I'm HIV negative, result is negative, we just pick it like that. You have to think twice. You understand now? The probability that it's negative is low compared with somebody in Osun. I don't know if you understand me now. So if somebody gets the result in Osun and they say, his result is negative. Yes, it's like the probability that the person is negative, yeah, is high, that is negative. Now, when they say somebody, they now give somebody in maybe river and I say, hey, your test result is negative. You still have to go further. It may not be negative. So, because of the prevalence of the disease, so when the prevalence of disease is very low, even a highly sensitive test will have low predictive. So the low predictive, the predictive value of HIV tests now all over the nation differ. Each state has its own predictive value, but the sensitivity is the same for a particular test. For a particular test, each region, every location has its own predictive value, but the sensitivity and specificity, they are the same. I don't know if there's any question that effect. That's what I just did. So look at the plot. Positive predictive value and disease prevalence. Can you see? As the disease prevalence increases, the positive predictive value will increase. That's so that the prevalence decreases, the positive value will decrease. If we plot, say we superimpose negative predictive value now, it will be in the opposite direction. So I think we move further. Yes.
So this looks different from the slide before this, because in the slide before this, it was like I think there was an inverse relationship.
I can't hear you very well. I don't know if your voice.
Can you hear me now?
Yes, go on. And my speaker is at the highest.
Sir.
Yes, speak loud. Or increase your own speaker.
Okay, I was saying that from my speaker is on the highest too.
What's that? Go on.
I was saying that in the slide you showed us before that graph, there was an inverse relationship between prevalence and positive predictive value. That's what I thought I saw. With increasing prevalence, there was the positive predictive value was low, while for the specificity, it was a direct relationship. So with increasing negative
What was
predictive
happening to the
value.
prevalence?
Maybe
are
you
the
can
one
just show
missing
the
it up.
slide.
You are the one missing it up. What was happening to predictive value? This is the slide
So
now.
just that slide.
And this slide now.
So no, the one
as you are
before.
going
Okay,
down, as you are going down.
Okay, look at this scenario C.
Okay, well, let me ask you the first scenario. What is the prevalence?
Yes, look at scenario C. The positive predictive value is 25.4.
Mm-hmm. And what happened to the prevalence?
In the first scenario, the prevalence is 50%, sir.
The prevalence of the disease is what?
No, in scenario A, the prevalence is 50.
And what is the positive predictive value there?
97.1.
Okay. Scenario C, you are talking about what is the prevalence?
Hello?
The scenario C, you are talking about what is the prevalence there?
Okay, the prevalence is 1%.
And what of the positive predictive value?
Okay, I just saw it now.
So you
I was
see,
looking at the lower one.
They move in the same direction. The prevalence become low. The positive predictive value go down. It's the negative predictive value that move in opposite direction with the prevalence. And that was why if let's say we plot the negative, the slope will be negative. It will slash down. It means that the prevalence increases, the negative predictive value will decrease. So the positive predictive value, it moves in the same direction with the prevalence. As the prevalence increases, the positive predictive value increases. As prevalence decreases, the positive predictive value decreases. Is it clear now?
Yes, sir. Thank you, sir.
Now, let's move ahead. Now, you will see something from what we have just, you discover that the somehow, we know that the prevalence has nothing to do with specificity, sensitivity. The prevalence and positive predictive value, they are the ones that have issue with themselves. But what have the sensitivity and positivity have issue with is your cutoff. It's with you, the one that determines cutoff. If you try to increase the cutoff, the value, if it's a particular condition that as the value increases, the person is likely to have the disease. If you increase the value, you get less people. If you having the disease, if you reduce the cutoff, you get capture more people. So when you reduce your cutoff, they say the test is more sensitive, but the specificity will be lower. So as you try to increase your sensitivity by reducing the cutoff point, you reduce your specificity. If you increase your cutoff point to reduce your sensitivity, you increase your specificity. Can you see that? If it's the other way, maybe it's a test that as the value increases, you are less likely to capture, like anemia now. When you increase the value of your cutoff for anemia, you are likely, when you reduce anemia is when the hemoglobin concentration is lower, says anemia. So if more people, you try to increase the cutoff, if you want to make it to be sensitive, you increase the value. Yes, I mean, you say you can now say that even PCV of 35% is anemic. You capture more people. So you move in the opposite direction. So what I just want to establish here is that the specificity and sensitivity move in opposite direction based on the movement of your cutoff. Now, How do we determine this cutoff? This cutoff. Okay, before that one, from the statement I just said now, when a test is highly sensitive, it's good for screening. I didn't put it on that. When a highly sensitive test is good for screening. A highly specific test is good for confirmation. So when something you do a test and you validate a method and the sensitivity is not as much as specificity, the specificity is higher, it's not good for screening, it's better for confirmation. But if the sensitivity is very high, it's good for screening. What do I mean? Screening means the first one you did to get as many people. Then confirmation is to see, okay, after you have done the screening, you want to confirm if the person actually have it. Because the issue of predictive value has come in. The issue of predictive value has come in, makes you want to be, because the predictive value, different locations, we have different predictive values. So the same result doesn't mean the same thing in different locations. So we now do confirmatory tests. But the sensitive, highly sensitive test is good for screening, while highly specific test is good for confirmation. In some situation where you have tests, you cannot actually, both of them, those tests, the specificity and sensitivity are almost the same. Maybe you can say they are high or no. You cannot really say one is highly specific over one is highly sensitive over one. So what people do, you have two tests like that. If you run them concurrently, parallel, that is parallel, you want to increase the sensitivity when you run them concurrently. But if you want to increase the specificity, you now run them in series. So that's another way of doing it. So when you do a parallel test, you want to increase your sensitivity. You want to capture as many people. So parallel tests mean that at the same time you are doing the two type of whichever one is, that should that whichever one is one is positive. But if you actually, or if you do it, you do the test in series. Especially it may be the same time you say on different occasions to confirm. Because if somebody, you do a test now and the person is positive, if it's by mistake that it didn't happen, just by chance, if you do it again, it may not be positive. So you have done it in series. So let's do it again. Maybe it's the same test, or another test that is almost the same sensitivity, but you repeat it. You know, it's okay. Even some people go to another lab to do it. So it's like doing tests in series. So when they say you have this, no, I'm not sure. You go to another lab to try, if that is the case. So I think we move on. Any question? Now, the cutoff issue. How do you determine? We already know that from the previous slide that if you are too generous with your cutoff, you reduce the value. You want to get as many people as possible so that your test can be sensitive. You capture a lot of people also that don't have the disease, and you say they have it. And that's implication based on, depending on the type of disease. Disease like cancer, HIV, you don't play that up front, because if you say somebody that doesn't have HIV, you know that that information can kill the person immediately. So, or cancer that, especially we don't even have treatment. If you don't have treatment, it's better you don't say the person have cancer. Unless you know that there's a treatment that you can give. So if somebody doesn't have cancer, and he has cancer, you know, it's a dangerous thing. So that type of test, you don't want to lower the bar. You want to be sure You want to be sure. Your cutoff, you don't just say you have it. But there are some tests also that there are some conditions that they are dangerous, but there's treatment for it. Yeah. So it's better. Somebody that doesn't have it, if treating, even by mistake, if treating, it didn't do any havoc, it's better to lower, to use highly sensitive tests to lower the bar so that you can capture as many people and treat. Even in the process, you may mistakenly treat the person, since number one is known, the treatment is known, it doesn't cause havoc, and it's available, it's cheap. So you can treat as many people as possible. You can screen, diagnose as many people. In the process, even though you misdiagnose and treat some people, they don't have it, it doesn't, it's still okay for the society than the other type. So it now depends on the type of test. Now, the issue, how do you even know the right cutoff? So the right cutoff now will now be a cutoff that will maximize your decision, that will take as many people that have the disease and say they have it, and the people that don't have the disease and say they don't have it. That's the type of test you look for. Now,
So what type of test you look for? I didn't get that far.
the test you are looking for is the test that will pick as many people that have the disease and say they have it, and as pick as many people that don't have the disease and say they don't have it. It has a large, a big, a good discriminative power. The discriminative power of the test is the ability of the test to separate the people that have this disease and say they have it, and say they have positive result, and people that don't have it and say they have negative result. You get the picture now. And it comes to the concept of likelihood ratio. And this concept, and that's what leads us to the ROC we are looking at. I think the Second World War, the soldiers tried to use telecommunication to send radar to send signal. So the war receiver's operating characteristic of is borrowed from the telecommunication. They try to look at it. When they are sending, signal with their radar, you get signal, you get noise. You cannot perfectly have signal without noise. There will be background noise. But they now try to maximize. What do? They try to plot to know when the signal is maximum and the noise is minimal. Do you get it? If we are to apply this logic to our own now, so we have 3, 4 possible options here on our result. We have true positive, true negative, false positive, false negative. You are looking at it. Which one is signal? Which one is signal? Which one is noise? Because out of the 4 now, one is signal, one is noise. Which one is signal? Which one is noise? So food for thought. It's a workshop. Let me get response. Out of what we have here, we have defined all of them. True positive, the one that have it and the test say they have it. True negative, the one that don't have it, test say they don't have it. False positive, the people that don't have it, test say they have it. False negative, the people that don't have it, test say they have it. And the people that have it and test say they don't have it. False negative. So which one is signal? Which one is noise?
I didn't get that part.
True positive should be signal.
True positive, yes. True positive is signal, yes.
I think I went off at some point.
You went off. Who took you off? What we are saying is that if you get when I talk about telecommunication, when you say signal, you get
signal. My internet was going off.
I said, did you get the explanation I gave about signal and noise? In telecommunication, they try to maximize the output because when they try to maximize the output, when they say they try to when they watch their radar, they are trying to get signal and noise also come.
Hello?
So the best and they are tuning. You are not hearing me. So that's your own. So it's your own hand. You watch the video. It's your own, because I'm explaining to you again, but you are not getting me. It's your own side. So somebody has said that true positive is the signal. What is the noise? What is the noise?
No, I can hear you.
Even my own went off. Yes, I can see. Hello? Can you hear now?
Hello, sir. Yes, sir.
You can hear me now? Yeah, I'm not muted now.
Yes, we can.
Yeah,
Yes,
it's not responding. Me, I will move ahead because I'm trying to explain, because you are taking us, but I'm
Yes,
trying to
sir.
explain to you.
Go ahead, we can hear you.
No, we can. No, we can hear you, sir. It's just that
What
I
I'm
think
not
there's a
saying,
delay.
I said that when in telecommunication, when they mount the radar, they will be tuning to get signal. The signal also come with noise. So if you say when you are tuning radio, you are hearing, but there's some noise. You are trying to tune so that you minimize noise and maximize signal. You understand me now? So there's a tune that gives you the best signal and the least noise. So if you are to apply that particular scenario or logic to this diagnostic test now, we have 4 options when the result comes out. We have true positive, true negative, false positive, false negative. I say, which one is the signal? Which one? Out of these 4 scenarios, one is signal, one is noise. Which one is signal? Did you get it now? Because if you don't get it,
Yes,
That is an analogy, just an analogy.
it's an analogy, yes. Because if you don't, it's a logic. If you don't get it, you will not understand the ROC. You cannot understand the ROC. So this person that says she didn't understand, do you understand it now?
Yes, sir.
So which one is the signal? Which one is the signal? That's why I want to throw it open for discussion. Which one is the signal?
It's too positive.
True positive. Yes, somebody has said it right. Yeah, true positive is the signal. Which one is noise now?
True negative.
Noise will be the
True negative.
And no, sorry.
How can true negative?
That's have to see.
Okay, let's debate it. Yes, I agree that false positive is false positive
False
now.
positive.
That's the noise now. Somebody, they say you are HIV positive and you are not HIV. It's noise now. It's noise. So true positive
is like true negative then.
True positive is signal. False positive is noise.
Can we debate it? So that means in another scenario, the true negative can be a signal, and then the false.
Which scenario? Which scenario now? Which scenario? Because the issue is that listen to me. Listen to me. If you look at that table, yes, look at that table. The result that give out that somebody has HIV is true positive and false positive. The other one is nothing. The other one, no. Oh, the result is negative. So the two negative, positive results are the one that either. So one is signal. Somebody that has HIV, you say the test say he has HIV. That's a signal. Someone that doesn't have HIV, the test say he has HIV is a noise. I don't know if you understand me now. So when you are talking of signal and noise, so because it's the positive result that sends out something. The negative result does not send out anything. The positive result is the one that sends out the true and the false. Can you see now? It sends out the true and the false. The one that have it, that is the true. The one that don't have it, that is false. So we have agreed that true positive is signal, false positive is noise. Now, if you look at the left side of the slide, where I talk about adding them vertically, you will see that that false positive, which is the noise, is actually 1 minus specificity. You can write because false positive plus specificity, because specificity is the true negative. They add up to 100%. So the false positive can be written as 1 minus specificity. So if in trying to get the best two now, It will be a situation if you divide this signal over noise. The signal is maximum, the noise is minimal. It should be able to be big such a way that it will be greater than 1, not only greater than 1, it will be big. So if you make the signal to be numerator and the noise to be denominator, you expect a big value. If the that will be the best, where you maximize the signal and minimize the noise. You make noise. So that would be the best. So when you divide the true positive, which is the sensitivity, you know the true positive is sensitivity, over 1 minus specificity, which is the false positive. That will be sensitivity over 1 minus specificity. That is what we call likelihood ratio. That likelihood ratio is the one that the one that have the highest. If you have different cutoff now, you now begin to tune. You know, the tuning means you are changing your this dotted line, vertical line that you are used to know the cutoff. You change the cutoff. If you are trying to vary the cutoff, for each of them, there's a value for true positive and false negative. So you know there's value for signal and noise. The one that gives the highest likelihood ratio is the best cutoff. So I told you the first time I plotted this was when I was a senior registrar. I read about it a week ago then, and there was one project that Professor Ajiro Shuku they were doing. He's a professor of medicine in Lut. So my HOD, Professor Nojale, was one of the panel member. So they sent it in to him to analyze. He now sent it to me to analyze. I didn't even know. He just sent something to me to analyze. When I analyze it, the next time, so when I sent this out to him, I didn't even know where the work was from. So he said to them, they now send him a mail, say, yes, we have presented the result to the panel, they are okay with it. Can we do ROC? He now sent the mail to me. ROC. This is what I read last week. So by that time, I wasn't even using SPSS, I was using EpiInfo. And EpiInfo, you doesn't have it. I don't know if the new version have it now, because I've let it for long. So I have to. So I understood the concept. I now read again about it to understand the concept. What I had to do was to be looking for different cutoff for that thing. I will determine cutoff, I'll calculate the sensitivity, specificity, I will do sensitivity over 1 minus specificity. I did it and now use Excel, and now enter it into Excel, and now plotted the graph. But now, the computer, that's moving the cutoff now. It's just a concept for you to understand. But the computer give it to you. So it's a graph. We're going to do that. So what it will happen is that it will now plot. Look at the graph. It will now plot sensitivity as vertical, 1 minus specificity, which is so sensitivity is the true positive, 1 minus specificity is the false positive. Now, the best one will be the most uppermost and leftmost part of the curve. Okay. So which one? Who knows? Who can tell? This graph now? Who actually know where is the most leftmost and uppermost part of this graph? Because that is when you divide the sensitivity over man or specificity, give you the highest value. Who can show it? Who from the graph can you spot it, the most leftmost and uppermost?
It's at the intersection, sir.
Which intersection? Where?
Between the blue and the green line.
Oh, okay. That, in fact, as you just say intersection, let me explain some other thing. This graph you see here, the data we're going to use is what I use to plot the graph. But there are some other one. This thing you are seeing now. So let me explain something further. If you plot this graph, you know what? The area under this graph is 1. If you look at the scale now, because the vertical is the higher, you know, it's probability now. And when you are mentioning either you express as 100 or 1. So it cannot be 1 more greater than 1. This one cannot be greater than 1. So 1 times 1, the area will be 1. The area under the graph is 1. If you plot it and the graph is along the diagonal, what it's telling you is that it's gambling. It's telling you that this test, this discriminating power is useless, because it's telling you that 50% of the time, he will tell you, he will be able to discriminate between the people that have it. 50% of the time, we say, okay, the people that have it, have it. The people that don't have it, they don't have it. The people to be honest, that will not do that. So that type of test is gambling. If it's below that diagonal, that shows that in fact that test is not even doing, it's not even, in fact, it's not even telling you anything. Most of the time, he will even tell the people that have it, they don't have it. He will even tell you the opposite. That was telling you. More of the time, we even tell you the people that have it, they don't have it. The people that don't have it will say they have it. That shows that that is. But if it is along the diagonal, it means the gambling is just halfway. But once it's above the diagonal, that shows that it's able to tell you that, able to this most of the you have signal, give you signal more than noise. So if it's below the line, it's give you noise more than signal. But this one is, the more, the higher it is. If it is perfect, if the graph is perfect, that it will tell you that all the people that have it, they have it. All the people that don't have it, they don't have it. That will reach number 1. That blue curve will end at the diagonal at number 1 up. It has covered the whole graph area. That will be area under the graph will be 100. Because the area, the probability that is able to discriminate, the discriminating power is the area under the graph. So the more the graph is going to the upper and left side, the more the discriminating power of the test. So let's plot it, because in the process of plotting, you get to understand some other things.
Can you use your point?
Yes, what do you say?
Can you use your pointer? Now I want to use your pointer.
Yes, this is this blue line, and this graph is going to this corner here. That shows that the area, because the area under the graph is the area under the blue, down. Yes, I mean now it may be 0.987. The more the area, the more the discriminating power of the test. That is, the ability to discriminate between people that have it and people that don't have it. That's mean that the test is good. So okay, if it reaches this place, that shows that it has covered discriminating power is 100. What is
that is blue.
Yeah?
That's if the blue line covers.
Yes, that is the graph now. Once the blue line, okay, it reaches, that shows that it's everything. The area will be 100. It means that it's perfect in discriminating. That shows that all the people that have the disease, you will always tell them they have it. All the people that don't have it, you always tell them they don't have it. So any positive result means that the person has it. Any negative result means the person don't have it. That's what doesn't have it. That's what it means. Now, let's plot it, because if we plot, in the process of plotting, we're going to see a lot of things. You understand the way it works. So let's plot. You see something, I think the term is as ROC. Does anybody want to share, or I should share? The data set is ROC.
The one I saw was the Altman. Or was it the one you sent?
No, it's part of what I sent before now. Part of all the people, all the one I sent. ROC curve is there now. Okay, maybe I should share my own. Any question before we run into any clarification? Okay. Dr. Alfred, you want to talk? Dr. Erua. Dr. Erua.
Hello?
Any question?
Hello, I can hear you, sir.
Any question?
The only question I have is the ROC curve that you just described, is it representative of the likelihood ratio?
It's the likelihood ratio that is plotted here now. Is the likelihood ratio that is plotted. Sensitivity over 1 minus specificity. What you have is the likelihood ratio on that graph. That graph is likelihood ratio is plotted. The highest one will be the is the likelihood ratio. The sensitivity over 1 minus specificity. You now plot sensitivity at vertical, 1 minus specificity as the horizontal. Yes, thank you.
Okay.
So this
the
is a
value
data set. Yeah. What do you say?
I said the value you get there is the same thing you get when you say the AUC, that's the area under the curve.
Yeah,
That's
yes.
the same value you get.
Yes, you will see. No, we're going to see the area will come out now. The area will come out. You know, you have ROC in your work also. Okay. Now, this one, we have obesity. You want to validate obesity as determined by mean arm circumference. And the gold standard is obesity by BMI. Yes, I'm now. So obesity by BMI, you have already known people who are obese are not obeyed by BMI. So, and the people that are obese, we have coded them. If you go to check the variable view, you see the people that are obese, we coded them 1. You must understand that. Check this. Can you see obesity? Can you see yes 1? No 2. Yes, I'm now. Because that's gold standard. There, that's not what you are validating. You have to, even if you enter the obesity by BMI by the value there, you have to first of all divide it into 2 like that and say, okay, these are the ones that are obese, these are the ones that are not obese. Because that is all what you are validating. You have to first of all tell that these are obese, because that's the gold standard. But if you look at the BMI, go to the data view now. You see BMI, mid arm circumference. Please, is the value you put there. You want to know at what cutoff point of mid-arm circumference you say somebody is obese. Is it clear now? So we want to validate it. So go to analyze now. Go down, you see the last option is ROC curve. Last option there. Now, the test variable is, yes, the test variable is mid-arm circumference, yes. Yes, what you did was right. The state variable is the obesity by BMI. And what is the value? Put 1 there. Because people that are obese, you have coded them as 1. Put 1. Now, click on diagonal. If you want the diagonal line to be in the graph, you click yes. Now, there's some other thing you want to show. Go to option. Click on option. So, you see the option here. If you look at the first option, it include cutoff value for possible classification. If you look at it, there are some tests. Like if you say you are doing like a blood sugar now. They say blood sugar 126 and above is diabetes. But that's some they say above 126. So if you want to include that particular value as part of it, can you see? That's the option. Include cutoff value for positive classification. Then exclude cutoff value for positive classification. Can you see that? If you don't want to include it, you want just want to say anything above this value to the second option. Can you see that? Then you see the other one under test direction. You see the other one under test direction. You will see larger test result indicate more positive test. Like this one now, the more the up mid arm circumference, the more positive. Yes, which is true. But if it's, let's say you is anemia and you want to diagnose now for hemoglobin concentration or PCV, if you put this one, it's not a direction because the smaller test result indicate more positive test for that one. So the options are there. It's you as the person that is doing the research, you should know. You are analyzing, you should know, because computer will not know it for you. But they just put some default value, because most of the time it is when the value increases that the disease is there. That's why they put that one. You can change. So every other thing, just leave that one. 95% confidence. Just continue. Just continue. So okay. So share the result. It's like there's something we didn't show. You have to go back. Show the result first. Show the result. Yeah, show down, go down. There's something you didn't. Can you see? You know when I told you what we didn't scroll down. Let me see. Is there any other thing? Okay, we'll go back. Let me explain first. Yes. Okay, go back to analyze. Don't stop sharing. Just go to analysis here. Analysis here. From here. From the VR window, you can access analysis. Go to analyze. Go back there. So that's something. Then coordinate point of the ROC curve. Click on that. That's the one. Clear. Yes. Yeah, click OK now. Click OK. Yes. So scroll down. So let's see what it gives you. Scroll down. You see after the plot. Go down and see. Go down. Yes. Can you see? This coordinate. Let's see. Scroll. Let's see the scroll up. Let's see the length of this coordinate point. It's okay. It's okay. So what he does here is that he just tries to tell you how the computer plotted this thing. You see the first column, positive if greater than or equal to. It's telling you the cutoff, different value. Around use all the different value as cutoff. You know, iteration. You know, that was what I did. I told you with hand. If you want to plot it, that's all you have to do. You have to set different cutoff and calculate the sensitivity and calculate the 1 minus specificity. Can you see? Calculate the sensitivity, calculate the 1 minus for each cutoff. Let's see the one. If we want to actually know which one has the highest likelihood ratio now, it doesn't show it here, but if you want to show it, click on this table. I'm going to put it on a Word document. Click on this table. Right click on the table, copy. Open a Word document. You can open outside Zoom and share it with us. Open a Word document and paste it on it. And share the Word document with us.
Okay, sir.
Yeah. What I want somebody to be doing is so that you will be learning it. So because if I'm doing it, I'll even be faster, but a lot of things you will not get. And somebody also, if you are not sharing with us, you can be doing it. Share the Word document where you put it. It's taking time to share. Yes, that's great. Yes. Now, you can put something on the table, highlight it and put the grid line so that people see it. No, there's a place on it. I hear the table. There's a plus there. You can click on it to highlight it. No, it's not highlighted. There's a plus on that table. The beginning of the table. Go to the beginning of the table. Okay, anyway, go to the beginning of the table. Go down. At the beginning of the table. Hey, at the edge. Those things, those coordinates, something they are. Is that the beginning? Scroll up now. Scroll up, because all those other things they are inside the table. The beginning of the table, why your computer not showing? It's supposed to show us one plus. Anyway.
Yeah, it's supposed to, but it doesn't have it. Let me just put the
it's your computer. Don't worry. Okay, no problem. What we do, I just want you to copy it. I want you to copy and go and put it on Excel. because we want to do the something. You cannot directly from that SPSS to paste on Excel. It will not allow you. That's why I ask to bring to Word document. So you now copy, go and put on Excel. Are you there?
Oh, it's not allowing me do.
Don't worry, I will do my own now. Don't worry, I will do my own.
Okay, sorry.
Because okay, I didn't bring this. I didn't read my own. I'm trying to read my own now.
Dr. Gulo, stop sharing so that we can see your screen.
What is it? No, I will share now. I'm extracting the data. Okay, Gulo, stop sharing, I will share now.
Okay, sir.
Yeah. Yeah, let me share now. So this is my own, the same thing. So just quickly run it. ROC. So you see it. So this is the one I copy. Let me share my Word document. Can you see the Word document? Can you see my Word document?
Yes, sir.
Yes, sir.
Yes.
Can you see what I was saying? That's dots. Can you see? You can easily select it and put the grid line so that I capture. What I want to put here. Can you see now? So I want to bring out so I want to go and put this one on Excel now and copy it and put on Excel and copy. So I will open Excel again. I will share the Excel with you. So can you see the Excel now? Let me paste it. Can you see the Excel?
Yes, sir.
Yeah, I pasted it. Usually I pasted it on Excel. You know, Excel will do mathematics for you. So if you see the first column is the cutoff, the second column is sensitivity, the third column is 1 minus specificity. Now, you know our likelihood ratio is sensitivity over 1 minus specificity. So just from here, just say equal to, for the first one, equal to sensitivity divided by 1 minus specificity. Just enter. So you drag it down. When you select and drag it down, you calculate for all of them. Can you see now? You calculate, can you see? You can calculate the value. So you know the first cutoff now will correspond to what's the highest likelihood ratio. So sometimes you may have to sort for you so that you don't miss it. But I can see the highest likelihood ratio here is 16.0. Can you see it?
Okay, yes.
0.06.
Yes, that's the largest, highest, 16.06. Yeah, the highest likelihood ratio. Can you see? If you check, there's no one bigger than that. So now you may have to sort just to know which one is the highest. That would be the best. So the cutoff that give that value is the best, and the cutoff 28.5 Can you see? 28.5. Can you see? 28.5 is the cutoff that gives sensitivity of 0.241 and 1 minus specificity of 0.8. Now, if you want to know the specificity, now you remove the 0.015 from it. It will give you the.
Excuse me, sir.
Yes, sir.
I think there is 18.1 under the 16.
Okay. Okay.
Okay. That's true.
Yeah, you are right. Yeah, that's right. Yes, that's the one. 29.5. I think that's the highest. 80.1. Yes. If let's say we have sorted, if you sort, if you wanted to sort, you just put your hand that highlighted something. If you want to sort, so that source ascending or descending will be able to give you. Yes. Let me see. Filter. So it has sorted. Can you see now? It has sorted. Can you see the last one 80 point? So once you saw, the corresponding value is 29.5, 80.1, 79.5. So that is the. If you look at it, the sensitivity is 0.181 and specificity is 1 minus specificity is 0.01. So it's telling you that the sensitivity is very small, but the specificity is very high because the specificity will be 0.999. Are you following now? The specificity is 0.99. Why the specificity is 0? That shows that the 99.9 is the specificity, 99.9%. Why sensitivity is 18.1%. That is so. Are we following?
Yes, sir.
Because how did I get 1.9? You know,
yes,
what you have here is 1 minus specificity. So 1 minus specificity is 0.01. If you want to get specificity, remove this one from 1. It's showing that that is highly specific. That is not sensitive. It's not a good for screening, test for screening. You cannot be using it and say you are using that type of test to screen for obesity. It's not sensitive, but it's specific. If you have done obesity before, you have used highly sensitive test to screen, you can now use it to confirm. So among the people that they say has obesity, you now come and do their mid-arm circumference, and that's okay. Anybody that now have mid-arm circumference that is more than this is obese. So after you have done screening, it's only the people that you have already screened that you now do the mid-arm circumference for. It's good for confirmation, but it's not good for screening. But now let's go back to the test, to the output. Now, can you see the output now? Are we together?
Yeah.
Yes.
You are not answering me. You are not. So, when we're talking of the.
We are with you.
Yes. So, when I was talking of the rightmost and uppermost, what is trying to tell us is that if you look at the sensitivity here, the sensitivity here around, we are talking of 0.18, 0.18. That was the sensitivity here. If you look at it, all this one, you see them up, but they are not right, left. So the uppermost and leftmost is around this place. In some study, you can see them conspicuous. If the sensitivity is very high, it will be up here, conspicuously. You see this thing will be here. What did you say?
And I saw you were using your arrow because I was
okay, yes, I was using my touch. Okay, now let me just explain. You will see also some of the thing that came out is the area under the cuff came out. Can you see? Area under the cuff is 0.757. Can you see?
Yes, sir. Yes, sir.
So those are the things. So those are when you are bringing the result out, you bring area under the cuff out, you bring the sensitivity, specificity, so you can know from the. So you now, if you The same thing now. You can go and use the cutoff point of 29.5 and divide and I say obese, not obese, and now do the cross tabulation. And it still confirm, give you the sensitivity that and specificity. If you still want to now calculate their predictive value with it. Like for example, now we have already said that the right this thing is 20, the value that is 29.5. So if you go now, all you need to do is that you go to the data set, and say, okay, you go to data. If you go to data now, select cases. Are you looking? Are you seeing it?
Yes, sir, we are.
Yes, select cases. You know, mean arm circumference. Mean arm circumference. We are using equal to or greater than 29.5, right? 29.5 at the cutoff. You put it greater than or equal to 29.5.
Yeah.
You see? Continue. So if you go to data editor window, yeah, go and look at it in data editor window. Look at it. It has a so if you go to variable view, you'll be able to say, okay, this one is obese. I call it obesity with mean arm circumference. That is obesity with mean arm circumference. So you can remove this labeling and say yes. Mean just say instead of though it doesn't change anything, label yes, change. No, you change. So when you are done that, you can go back and remove from the data. You say select all cases so that if you don't do that, it has not cut those ones. So you have created that variable now. So you can now have your cross tabulation. If you go to analyze, are you seeing me? What are you seeing?
Yes.
Analyze, cross tab.
So wait. Okay.
Cross tab. So you know the gold standard, the gold standard, the obesity mark is the row now. That's your test. The gold standard. No, there's something. There's something I need to do. I need to correct something. I just remember now. In that data editor window, if you remember, so that you will not cause confusion. You will not cause confusion for yourself. In that data editor window, it's good to now change. You know, it's the 0 that you label those ones that are no. Change it to 2. No to 2. Yes, I'm now. And go back and all those, if you can do that, all you need to do is just to, if you say ascend, sort ascending, so that I can put them in the same place for you. Can you see now? I've sorted ascending. All this 1, I put 2. In all this 0. Yes, I'm now. I change them to 2. I'll tell you the reason. I'll tell you the reason.
Okay.
So if you look at it, we already know that not many of them are obese through that. So the no are plenty. I see. So I've labeled, yes, safe. So I've labeled the other one. So I can now go and do what I want to do now. You have seen it, right? Analyze.
Yes, sir.
Cross tab. Sorry. Cross tab. Obese. Obesity.
So
the BMI is the gold standard, is the column. The obesity through the BMI is the gold standard. Are you
okay? The BMI, so it's the gold standard that is put in the column.
So I go to, I don't need the statistic here. If you want to calculate chi-square, whatever. What I want.
Let her take out. Let her take out.
What do you say? Somebody is making. So I put row and column percentage. Just because you know that. Okay, don't worry. I will explain it. So that's all I need here.
I want to ask something, sir.
Okay, ask.
Okay, I want to say that if you switch this, like let's say you put the obesity in the row and the mark, will it give you a different answer?
It will give you the same, but you have to know that that's what you put. You put it there, it can be confusing. So it's good to follow the standard. It's just cheat it to the side. It may make you, that's why it's by convention, you do it like this. Yes, I mean, just like the way we usually.
Okay. You know me, I'm used to independent and dependent. I'm not really used to, I don't really know how this is done.
Okay, the outcome, the real thing, the outcome, the gold standard is the one that comes as the outcome. That's the real gold standard. What you are testing is the other one, is the coming at the row as the exposure. So the gold standard
so what you are testing,
at the vertical. The what you are testing is at the horizontal. So
okay.
I don't know. Let me show the result of the cross tabulation. Can you see now? Can you see my?
Yes.
Yeah, let me go there. Sir. So look at it. You will see. You remember our sensitivity is 80.1%. Is that not so? Look at it. You know?
Yes, sir.
What I want you to look at here is that if you look at it now, let me bring my hand. You will see that I put row percentage is within obesity mark, column percentage within obesity. Yes, I mean now. I told you before, the people that have the disease, they are 232 that have the disease. 688 are not obese in the real life. The obese is 232. That's the row column total. Then the people that are not obese, column total here. But the people that are obese by mid-arm circumference, they are 49. Can you see? The people that are not obese, 920. Now, if you remember, when we are calculating our sensitivity, we say that it's the same this 42 we are using to calculate sensitivity and positive predictive value. Is the same 688 used to calculate. No, it's not 688. It's 681. 681. You used to calculate both the specificity and negative predictive value. The only difference is the direction of the denominator. For this sensitivity now, 42 over 232 is the 80.1. Are we following?
Yes, sir. Okay.
42 over 232, 80.1%. That is the sensitivity. The 42 over 49, that is the 85.7. That is the positive predictive value. 681 divided by 688. That is the specificity. That is 99. You know that what we got the other 99, the specificity is 99%, which is 0.99. That is why 1 minus specificity is 0.01. So the specificity is 99%. The same 681 over 871 is the one that gives you 78.2, which is the negative predictive value. So what we have then is that we have a test that has low sensitivity, 80.1%, and high specificity, which is 99%. But the predictive value is.
So that means, in this.
Yes.
Hello. That means in this. Okay, that means in this you're using both. That means like in this particular type of analysis, you're using both of them, both the column and the row. That is both the, and one always gives the predictive, then the other one gives you either the sensitivity or the specificity.
It's not the always. You see, me, I don't like people talking from the blue moon. I want you to talk from understanding. You get the picture. I've already explained it that.
Yes, sir.
42, you know, when you say 42, 7, 49, 49 are people that have positive results from your test now.
With
mark. And the people that mark say they are obese. And the total is 920. Everybody is 920. But 49 are obese from your test, while 871 are not obese from your test.
Yes, sir.
But the gold standard, what it tells out of the 920, the gold standard says 232 are obese, while 688 are not obese. So when you are talking of sensitivity, your denominator is the number of people that actually have the disease. That is given by the gold standard. So the people that have the disease, they are 232. How many of them did this new test say have the disease? It's only 42. 42 over 300. That is the sensitivity. But if you want to now say, out of these people that total that this result is giving us that they have the positive result, how many of them actually have the disease? They are 42. 42 over 48. That is 85%. That is positive. So it's not a matter of whether row or if I change it the other way, it's still true. It's the only way that the way I will now interpret it will be different. So the issue is for you to understand. Because if you go, if you don't understand now, you see another person present a table in different way, you will not get what they are saying. You'll be confused. It's not a matter of row, but for you to maintain your DC, you want to maintain, okay, put this one at the column. You must know what to put at column, put at this. And if you maintain the convention, you will not confuse yourself. And why did I go back to change? If you look at it, change there 0 to 2. You know that if the obesity by BMI, I've already coded 1 and 2. So it means that alphabetically, it will first of all give me the column for 1, which is yes before, no, 2. If I've used 0 and 1, 1 yes, no, it will give you no first and yes later, because it's not looking at what to type there, it's looking at the value. The way alphabetically 0, when you are serially, 0 come ascending order, 0 come before 1. So that is why if I have done that now, what will have happened that it will have swapped the result of this obesity, the row for me, the obesity by BMI by MAP, mean arm circumference. It was swapped for me and make sure that this no comes first. If I have used no, I don't know if you understand me now. You put the no first and put the yes. So that is why you have to be. So that's why I rearrange them so that my no should be the second one, which is 2. Because each cell has its own address. This first is A, B, C, D. They have address. So if you mix it up, you misinterpret. Is there any question? That is it. Is there any question?
No, sir.
Yes, any question from any angle? Yes?
Yes, there's a question.
Okay, sir. Yes, sir.
Likelihood ratio.
Yes.
Sensitivity, all over 1 minus specificity, and it's the area under the curve. I know all those ones. But in layman terms, what is likelihood ratio? By definition, in layman terms, what does it mean?
Yes,
instead of using all the area under the curve,
the likelihood ratio is the ability of the test. Is measuring the discriminative capacity of the test. Discriminative is the ability of the test. The probability that the test will mark the people that have it as possible as having it, the people that have the disease are having the disease, and the people that don't have the disease, they don't have it. That's all.
Yeah.
So it's the ratio. So what is telling you that sensitivity is the ability of the test to say that somebody that have it. Is that not so? You are not following? Yeah, but the
no, I'm following now.
I'm answering you. Okay, yeah. 1 minus specificity, which is the false positive, is saying that people that don't have it. So how many times the likely ratio is telling you how many times the test will tell you that the people that have it more than it will tell you that people that don't have it. Does it make sense now?
Okay.
It measures how many times the test will tell you that the people that have it, and people that the people that don't have it have it.
That don't have
it, yes.
Okay.
The people that have the disease, how many times the test will tell you that the people that have the disease, the test is positive for them, than the people that don't have the disease, the test is positive for them. I don't know if you understand now. Because the test,
Yes, I
when the
understand.
positive result come, some is for people that have it, some is for people that don't have it. There, how many times the people that have it among those positive results is far more than the people that don't have it among the people that are positive. Is it clear now? That is what
It's
likelihood
clear.
ratio.
It's clear.
That's
It's
what
clear.
likelihood ratio does.
Okay.
Any other one?
Hello, Dr. Duro. Yeah.
Yes.
Okay. Yeah. Thank you very much for your efforts. Yeah. Okay. So, in other words, the reason for ROC is actually to how would one summarize the significance of ROC?
But
So,
something
of
is
what
making
purpose
noise in your
is
background,
it?
Dr.
Yeah.
NS. Something is making making noise in your background. It's disturbing us.
Okay. Okay. Yeah, let me just see that.
And you have to on your
Okay. So
product.
I was just going to ask.
Okay.
Okay. I was just going to ask in layman's term, what would one say is the role of ROC, receiver operating curve? Is it basically to determine? I mean, how does one? Because sometimes
Yeah,
we see
it
publications.
just,
I mean,
what
these things
the,
is
yeah,
cited in publications.
is just giving you the picture, mental picture of that likelihood ratio. You know, inside it now, you're able to see area under curve. It's also measuring the discriminating capacity of the test, ability of the test to separate that have it from that don't have it. So it give you, and pictorially also, you can locate that point also where the likelihood ratio is
on the curve.
Yes, maximum. Yes. You give a mental, the brain record information. You are a neurologist now. The brain record information in picture, not in letter, not in this, but it's in picture. So when you have mental picture of it, you'll be able to understand. Yeah.
Yes, it's okay. Thank you very much. Yeah.
So any other one, any other comment or any other question? Okay. I hope some people are not sleeping in their house because some people, since we are not seeing the faces of people, some people are sleeping already.
Yeah, some people are not sleeping.
Okay.
Yeah,
we are awake. I can't be sharing that.
How can you sleep? How can you sleep under ROC cuff?
I
said it's not possible to sleep under ROC cuff.
Okay. Okay. Let me.
So, sir,
yes,
that means the.
Go on.
So, just to confirm again, so it is the uppermost leftmost.
Yes, point. That's the point.
Point. Okay.
Yes, in the graph.
Uppermost left.
But uppermost leftmost it doesn't mean there has to be up. Leftmost is there. Uppermost and leftmost. So leftmost. Yeah. So it may not really mean the uppermost now. Uppermost and leftmost. It's only that because the sensitivity of this one is very poor. That's why you cannot see conspicuously. If it's other something, I don't know if Dr. Irua, your study, I don't know if your own was very conspicuous. I think let me check some people's work here. Let me check because that person that we did Atman something for also, we plotted ROC for that person.
And so that means, and in this case, the area under the curve is it which part? Is it the upper part? Is it the part above the blue line or the part below the blue line?
They say area under. How can it be above the blue line? And they say area under the curve. Okay. So there is the area above the curve.
Yes.
Area below the blue line now. Area under the curve is below the blue line. Yeah. Right. So I want to show Tahir's work.
Thank you very much.
Welcome. Tahir's work I want to show because I plotted the ROC also. I don't know if it's very. Okay, let me share this. So this person that did, can you see what I'm sharing? This person that did that work on European stuff. try to use TCP to see if you will do the same thing, transculating bilirubin estimation, to see if it's measuring the same thing as serum bilirubin. So can you see the ROC now? Can you see?
Yes, sir. So if asked to interpret this curve, how will you now interpret it?
It has area under curve. I think look at the area. You cannot quantify better. If you look at it, it's better. You can say that the area under curve is more than the one we just did. So this place, look at this dot, will be the uppermost and leftmost now. Can you see this place? This is the uppermost and leftmost point. So that shows that the sensitivity of this one will be around 0.6 something. Okay.
Okay.
Let me see if I wrote it here in the. We have other one also different. Can you see? We have one that even have sensitivity of 98. Can you see? So that's just it. So the implication is that if the more the area, the more discriminative power of the test. That is able to separate the people that have it and the true result, correct result from false result. So these are the many things we did for that person. So I think we stop here. Let me just stop recording.
Thank you very much.
Likelihood ratio.
Yes.
As I've heard of positive likelihood ratio and negative likelihood ratio.
Yes.
But I noticed that we'll be using the term likelihood ratio.
Yes, actually,
so
those one and it's just the opposite. Some people also plot 1 minus specificity over sensitivity. Hello?
Okay.
Yes. So they swap, yes.
Okay.
So they swap it. They swap the something. So or is it specificity over 1 minus sensitivity rather? Specificity over 1 minus sensitivity, they plot it.
Okay.
So they plot it, that's why they just time it.
So when we use the term,
what do you say?
So when we use the term likelihood ratio,
and that is sensitivity over 1 minus specificity, that is the likelihood ratio. But when they say negative one, they just inverted it.
Okay.
I should pause.